Hello and welcome. I'm so glad you're here with me tonight. Imagine standing in a museum looking up at the towering skeleton of a Tyrannosaurus rex. Its massive jaws, those powerful legs, the tiny arms that have launched 1,000 memes. This is what we think of when we imagine dinosaurs, isn't it? The apex predators, the thundering giants, the creatures that dominated Earth for over 160 million years. But here's something that might surprise you. What if I told you that T-Rex and its famous relatives represent just a tiny fraction of the story? What if the most fascinating dinosaurs weren't the ones Hollywood fell in love with, but rather the bizarre experiments in evolution that look like they were designed by a committee that couldn't quite agree on what a dinosaur should be? Picture a creature with claws longer than your arm, but that ate nothing but plants. Imagine a dinosaur with a skull so thick it could survive headbutting contests that would shatter concrete. Or consider a predator larger than T-Rex that spent its days fishing in ancient rivers, with a sail on its back taller than a grown human. These weren't fantasy creatures, they were real, and tonight we're going to explore their strange and wonderful world together. Before we begin this journey into the unexpected corners of prehistoric life, if you're finding this exploration intriguing, I'd be grateful if you'd consider subscribing and leaving a like. It helps others discover these stories. And there are so many more strange creatures waiting to share their secrets with us. Now, let's talk about why dinosaurs got weird in the first place. When we think about evolution, we often imagine a steady, predictable process. A species adapts to its environment, developing traits that help it survive. The faster gazelle escapes the lion. The bird with the better beak gets more seeds. It all makes perfect sense, doesn't it? But evolution isn't always so straightforward. Sometimes, in the vast laboratory of natural selection, nature tries something completely unexpected, something that, by all logical reasoning, shouldn't work. And yet, somehow, it does. The age of dinosaurs wasn't just one long, unchanging era. It spanned from about 230 million years ago to 66 million years ago. That's 164 million years. To put that in perspective, the time between us and T-Rex is greater than the time between T-Rex and Stegosaurus. During those incredible spans of time, continents shifted, climates changed dramatically, sea levels rose and fell, and entire ecosystems transformed. And with each of these changes came opportunities, ecological niches waiting to be filled by creatures brave enough, or perhaps desperate enough, to try something different. In the Jurassic period, around 200 to 145 million years ago, the world was warm and humid. Lush forests covered much of the land, creating a green paradise where plant-eating dinosaurs could thrive. But with all those herbivores came competition. Imagine being a medium-sized plant eater in a world where massive sauropods were already claiming the tallest trees, where armored dinosaurs were monopolizing the low-growing ferns. What do? How do you survive? This is where evolutionary experimentation comes in. Some dinosaurs developed bizarre feeding mechanisms that let them access food sources others couldn't reach. Some evolved extraordinary weapons or defenses that went far beyond what seemed necessary. Others developed body plans that seemed to defy the very logic of how a dinosaur should be constructed. And the fascinating thing, many of these experiments were wildly successful, lasting for millions of years. Consider the paradox at the heart of biological innovation. Every species is locked in an eternal arms race, not just with predators and prey, but with their own relatives. If you're a plant-eating dinosaur competing with other plant eaters for the same ferns and cycads, any advantage, no matter how unusual, becomes precious. Perhaps you develop a strange thumb spike that lets you pull down branches your competitors can't reach. Maybe you evolve a bizarre jaw structure that allows you to process tougher plant material. Or you might grow peculiar ornaments that help you win mates and pass on your genes. But here's the beautiful complexity of it all. These adaptations don't happen because the animal decides it needs them. A dinosaur doesn't look at a problem and think, I know, I'll evolve giant claws. Evolution is blind, working through random mutations and the filter of survival. Most mutations do nothing, or worse, harm the organism. But every once in a while, purely by chance, a mutation occurs that gives an animal an edge. And if that animal survives long enough to reproduce, passing that trait to its offspring, and if those offspring also survive to reproduce, then over countless generations, what started as a tiny advantage becomes a defining characteristic. The strange dinosaurs we'll explore tonight are the result of these successful experiments. They represent moments when evolution took risks that paid off, when the normal rules seemed to bend, when nature said, let's try something completely different and see what happens. Think about the world they inhabited. The Mesozoic era wasn't a static museum display. It was a dynamic, changing world filled with opportunities and challenges. During the late Jurassic, approximately 150 million years ago, the supercontinent Pangaea was beginning to break apart. This separation created new coastlines, new weather patterns, new habitats. Some dinosaurs found themselves in warming tropics, others in cooling highlands. Some inhabited vast floodplains where seasonal rivers carved through ancient forests, while others made their homes in semi-arid regions where survival meant adapting to harsh conditions. Each of these environments created different selective pressures. A dinosaur living near water might find advantages in adaptations that helped it catch fish or wade through shallows. A creature in a dense forest might benefit from features that helped it navigate through thick vegetation or defend territory in close quarters. Those on open plains might need speed or weapons or ways to signal to others across vast distances. And here's where it gets truly interesting. Sometimes the same environmental challenge led different groups of dinosaurs to evolve completely different solutions. When faced with large predators, some dinosaurs evolved armor, others evolved speed, and still others evolved to be so large that they became essentially invulnerable. When competing for food, some evolved specialized jaws and teeth. Others grew longer necks, and some developed tools, like strange claws or thumb spikes, that functioned like botanical Swiss Army knives. The dinosaurs we'll meet in the coming segments represent some of evolution's most creative solutions to the challenges of Mesozoic life. We'll encounter herbivores with thumb spikes that paleontologists initially thought were horns. We'll meet predators that abandon the typical tyrannosaur body plan entirely, becoming semi-aquatic specialists with crocodile-like skulls. We'll discover dinosaurs with heads built like battering rams, others with claws that seem absurdly oversized for their lifestyle, and some with armor so elaborate it turned them into living tanks. Each of these creatures tells us something profound about the nature of evolution itself. They remind us that there's rarely just one right answer to survival. They show us that what seems bizarre or impractical to our modern eyes might have been perfectly adapted to circumstances we can barely imagine. And they demonstrate that life, given enough time and enough pressure, will explore every possible variation, testing the boundaries of what's possible. Have you ever looked at something in nature and wondered, why would evolution create that? Perhaps you've seen a peacock's tail and thought about how impractical it seems, or watched a male deer carrying around an enormous rack of antlers and wondered why it would burden itself so. The strange dinosaurs we'll explore raise similar questions, but on a much grander scale. Why would a plant-eating dinosaur need claws that could disembowel a predator? Why would a creature develop a skull thick enough to use as a weapon in headbutting contests? What possible advantage could there be to having a giant sail on your back? Tonight, we'll seek answers to these questions together. We'll look at the fossil evidence, consider the scientific debates, and try to understand these creatures not as curiosities, but as successful animals that thrived in their worlds. We'll examine how paleontologists piece together the lives of creatures that died millions of years before humans existed. Using nothing but fossilized bones, occasional skin impressions, and the principles of biology and physics. Over the next hour and a half, we'll journey through 8 stories of evolutionary weirdness. Each one will introduce you to dinosaurs that challenged our understanding of what these ancient reptiles could be. We'll explore creatures that flew with 4 wings, giants with the strangest feeding mechanisms imaginable, armored dinosaurs with tail weapons that could shatter bone, and predators that rewrote the rulebook on what it meant to be a meat-eating dinosaur. But more than that, we'll explore what these strange creatures tell us about life itself, about adaptation, survival, and the incredible creativity of evolution when given millions of years to experiment. We'll see that normal is just a matter of perspective, and that every bizarre feature had a reason for being, even if that reason isn't always immediately obvious to us. So, settle in, get comfortable, and prepare to see the age of dinosaurs in a completely new light. Because the story of prehistoric life isn't just about the famous giants we all know. It's about the weird, the wonderful, and the wildly successful experiments that filled ecological niches we didn't even know existed. Our journey begins with a creature that was quite literally misunderstood for decades. A dinosaur whose most distinctive feature was completely misidentified when it was first discovered. This wasn't some minor detail that scientists got wrong. They didn't just misplace a bone or misjudge its size. No, they put its most remarkable feature in entirely the wrong place, creating an image of this dinosaur that persisted in scientific literature and popular imagination for generations. This is the story of the thumb-spiked herbivores, creatures that carried weapons on their hands while peacefully browsing on Mesozoic vegetation. And it all starts with a discovery in the 1820s that would fundamentally change our understanding of Earth's ancient past. The year was 1822 in the rolling countryside of Sussex, England. A country doctor named Gideon Mantell was making house calls, as he did most days. But Gideon had a passion that extended beyond medicine. He was fascinated by fossils, those mysterious stone impressions of ancient life that farmers occasionally unearthed while tilling their fields. According to the story, though historians debate its accuracy, Gideon's wife Mary Ann was waiting for him along a country road when she noticed something unusual embedded in a pile of rocks being used to repair the road. It was a large tooth, unlike anything she had seen before. When Gideon examined it, he realized this was no ordinary fossil. The tooth was enormous, with a distinctive ridge pattern. It belonged to something that had never been described by science, something that would challenge everything people thought they knew about the ancient world. But here's where our story takes an interesting turn, because when Mantell eventually found more bones of this creature and tried to reconstruct what it looked like, he made a mistake that would persist for decades. A mistake so fundamental that every illustration, every museum display, every scientific paper about this animal would be wrong, and it all centered on a single conical bone that he found among the fossils. If you're enjoying this journey through paleontological mysteries, I'd be grateful if you'd take a moment to like this video and subscribe. These stories of scientific discovery and correction are how we learn, not just about dinosaurs, but about the very process of understanding our world. Mantell named his discovery Iguanodon, meaning iguana tooth, because those distinctive teeth reminded him of a modern iguana's teeth, only vastly larger. He estimated that if this creature had teeth like an iguana, but so much bigger, it must have been an enormous reptile. And he was right about that. What he got wrong was that mysterious conical bone. Looking at this bone, sharp and pointed, about 10 inches long, Mantell made what seemed like a logical assumption. It was a horn, and where do horned reptiles typically carry their horns? On their noses, of course. Look at a modern rhinoceros, or imagine the dinosaurs that would later be discovered like Triceratops. Horns on the nose made perfect sense. So, in all the early reconstructions of Iguanodon, there it sat, a fearsome spike protruding from the creature's snout, giving it an almost unicorn-like appearance. For over 40 years, this is how Iguanodon was depicted. Scientists, artists, educators all showed this peaceful plant eater with a prominent nose horn. Museum displays featured it. Scientific papers referenced it. It became an accepted fact. And this, right here, illustrates something crucial about science that we often forget. Scientific knowledge isn't fixed and immutable. It's provisional, always open to revision when new evidence emerges. The correction came in 1878, in one of the most remarkable fossil discoveries of the 19th century. In a coal mine in Bernissart, Belgium, miners broke through into a cavern filled with an almost unimaginable treasure: skeletons. Dozens of them. Complete, articulated iguanodon skeletons, preserved in exquisite detail. It was as if an entire herd had perished together, their bodies settling into the ancient lake bed that would become this coal seam. When paleontologists carefully excavated and studied these remarkably complete specimens, the truth became clear. That horn wasn't on the nose at all. It was a thumb, a massive conical thumb spike attached to each hand. Imagine that moment of realization. 40 years of illustrations, reconstructions, and scientific assumptions, all rendered obsolete by this new evidence. But that's exactly how science is supposed to work. Now, with the spike in its proper place, new questions emerged. Questions that paleontologists are still debating today. What was this thumb spike for? Why would a plant-eating dinosaur need such a formidable weapon attached to its hand? Let's think about this carefully. Iguanodon lived during the early Cretaceous period, approximately 125 million years ago. It was a large animal, measuring up to 30 feet in length and weighing as much as 3 tons. Picture an animal the size of a large elephant, but with the body plan of a kangaroo. It could walk on all fours when browsing for food, but could also rear up on its hind legs when necessary. The thumb spike itself is a fascinating piece of biological engineering. If you could hold one in your hand, which you can actually do at certain museums with casts, you'd feel its weight and notice how it tapers to a sharp point. It's made of bone, covered in life by a keratinous sheath, much like your fingernails, but far more robust. The base of the spike would have been anchored by powerful muscles and tendons in the hand, giving the animal the ability to position it precisely. The most obvious interpretation is that this was a weapon, and indeed, a 3-ton herbivore equipped with 10-inch spikes on each hand would be a formidable opponent for any predator. Imagine you're a carnivorous dinosaur, perhaps an early ancestor of the famous Tyrannosaurs, and you decide to attack what looks like an easy meal, a plant eater calmly stripping leaves from branches. But as you lunge forward, this easy meal rears up on its hind legs and brings those spiked hands down in a defensive strike. Those spikes, driven by the weight and muscle power of a 3-ton animal, could cause devastating injuries. We can look at modern animals for comparison. Consider the cassowary, a large, flightless bird found in Australia and New Guinea. Cassowaries have a single large claw on each foot that they can use as a weapon when threatened. When a cassowary kicks, that claw can inflict serious, sometimes fatal wounds. Now scale that up to a dinosaur many times larger, with 2 spike-bearing hands instead of 1 clawed foot. And you begin to understand the potential defensive capability of Iguanodon. But there's another possibility, one that's perhaps less dramatic, but equally plausible. What if the thumb spike wasn't primarily a weapon at all? What if it was a tool? Think about how Iguanodon lived. It was a browser, feeding on the vegetation of early Cretaceous forests. These weren't the flowering plants we see today. Those hadn't evolved yet. Instead, Iguanodon would have encountered ferns, cycads, and conifers. Many of these plants would have been tough, sometimes protected by thorns or thick branches. A thumb spike could be incredibly useful for pulling down branches, stripping bark, or accessing food that other herbivores couldn't reach. Have you ever tried to break off a branch from a tree with your bare hands? It's difficult, isn't it? Now imagine having a built-in tool specifically designed for that purpose. A spike you could hook around a branch and pull with the full strength of your arm. Suddenly, food sources that were inaccessible to other dinosaurs become available to you. That's a significant evolutionary advantage. The truth is, these two functions aren't mutually exclusive. The thumb spike could have served both purposes. Just as many features in nature are multifunctional. Consider a lion's claws. They're primarily used for catching prey, but they also help the animal climb, defend territory, and even communicate through scent marking. Similarly, Iguanodon's thumb spikes could have been everyday tools for feeding that doubled as formidable weapons when necessary. What makes this even more interesting is that Iguanodon wasn't alone in having unusual hand structures. It belonged to a larger group called Iguanodontians, and several of its relatives developed their own variations on this theme. Consider Baryonyx, the heavy claw. This was a cousin of Iguanodon, but one that took a very different evolutionary path. Baryonyx was a meat eater, standing about 10 feet tall and stretching 25 feet in length, and it had claws, particularly on its hands, that were even more impressive than Iguanodon's thumb spikes. The claw on Baryonyx's first finger measured about 12 inches along its outer curve. But here's what's fascinating. Baryonyx appears to have used its claws for fishing. Fossil evidence, including fish scales found with Baryonyx, remains in the structure of its crocodile-like skull, suggests this dinosaur waded into rivers and used those massive claws to spear fish, much like a modern bear. So here we have two related dinosaurs, both with impressive hand claws, but using them in completely different ways. One is a herbivore, possibly using its spike for feeding and defense. The other as a piscivore, using its claws to catch fish. It's a beautiful example of how evolution can take a basic body plan and modify it in diverse ways to suit different lifestyles. Then there's Ouranosaurus, another iguanodontian from slightly later in the Cretaceous period. Ouranosaurus also had thumb spikes, though not quite as prominent as iguanodons. But what makes Ouranosaurus truly distinctive is the series of tall neural spines running along its back, forming a sail or hump. Was this for temperature regulation, display, fat storage? We're not entirely certain, but it shows how this family of dinosaurs was experimenting with different body modifications. The more we examine these thumb-spiked herbivores, the more we appreciate the complexity of dinosaur evolution. These weren't simple creatures following a predictable pattern. They were diverse, adaptable, constantly being shaped by the pressures of their environments. Let's consider the biomechanics more closely. When engineers analyze the thumb spike, looking at how it attaches to the hand, the range of motion it would have had, and the muscle attachment points, they can make informed guesses about how it was used. The spike could swivel somewhat, giving the animal the ability to orient it for different tasks. The muscles controlling it were substantial, capable of generating significant force. If Iguanodon used its spike defensively, it wouldn't have swung wildly like in an old movie monster fight. Dinosaurs were real animals bound by the same laws of physics and biology that govern creatures today. A strike would need to be controlled, powerful, and accurately aimed. The animal would likely have grappled with an attacker first, using its weight and strength before bringing those spiked hands into play at close range. If used for feeding, the motion would be different, hooking a branch, pulling it within reach, perhaps using the spike to strip away tough outer bark to reach the softer inner layers. We can imagine Iguanodon using its spike the way modern elephants use their tusks, as versatile tools adapted to their lifestyle. The story of Iguanodon's thumb spike teaches us something important about the scientific method. Science isn't about being right immediately. It's about being willing to revise your understanding when new evidence appears. Mantell made the best interpretation he could with the incomplete evidence available to him. A single conical bone, without context, without seeing how it attached to the rest of the skeleton. His nose horn hypothesis was reasonable given what he knew, but science is self-correcting. When those remarkably complete skeletons emerged from the Belgian coal mine, when paleontologists could see exactly where each bone belonged, the error became obvious. And the scientific community didn't cling to the old interpretation out of pride or stubbornness. They updated their understanding. That's how it should work. This same pattern has repeated throughout paleontology. Dinosaurs once depicted dragging their tails on the ground, like reptiles are now shown with tails held high for balance. Dinosaurs once thought to be slow and sluggish are now understood to have been active and, in many cases, quite fast. Dinosaurs once imagined as scaly are now known to have been covered, in many cases, with feathers. Each revision brings us closer to understanding what these creatures were really like. The thumb-spiked herbivores remind us that evolution doesn't always produce solutions we expect. Why a thumb spike instead of a horn, or larger teeth, or thicker hide? Because evolution works with what's available, modifying existing structures rather than designing from scratch. The ancestors of Iguanodon had hands with 5 fingers. Over time, one of those fingers, the thumb, became modified into a spike. It was easier, evolutionarily speaking, to modify an existing structure than to grow something entirely new. And perhaps that's the deepest lesson here. When we look at these strange features, these bizarre adaptations, we're seeing the fingerprints of evolutionary history. We're seeing how life builds upon what came before, sometimes creating solutions that seem odd or inefficient to our engineering-minded human perspective. But that worked perfectly well for the creatures that possessed them. Iguanodon thrived for millions of years with its thumb spikes. It spread across multiple continents. It survived, reproduced, and passed its genes down through countless generations. By any measure that matters, those thumb spikes were a success story. But thumb spikes and unusual hands are just the beginning of dinosaurian oddities. If you thought a conical thumb was strange, wait until you encounter our next subject. We're about to meet a predator that challenged everything paleontologists thought they knew about large meat-eating dinosaurs. A creature so bizarre that, when its bones were first discovered, scientists couldn't agree on what they were looking at. Some thought it was a crocodile. Others believed it might be some entirely new type of reptile. What they eventually realized was even more extraordinary. This was a dinosaur that had adapted to an environment most of its relatives avoided entirely. A giant predator that might have spent as much time in water as on land, with adaptations so unusual that debates about its lifestyle continue to this day. This is the story of the sail-backed giant, and it begins with a discovery in the deserts of Egypt. Picture, if you will, the year 1912, the desert of Egypt near the Bahariya oasis. The sun beats down mercilessly on the sand-colored rocks that hold secrets from a time when this arid landscape was something entirely different. A German paleontologist named Ernst Stromer is overseeing an excavation, and his team has just uncovered something extraordinary. Bones. Massive bones. But not just any bones. These belong to a predator, unlike anything known to science. As Stromer carefully examined what his team had found, he must have felt a mixture of excitement and confusion. The skull was elongated, almost crocodile-like. The teeth were conical, designed for gripping rather than slicing. And then there were the neural spines, bony projections extending from the vertebrae, some reaching nearly 6 feet in length. In life, these would have supported a massive sail running down the creature's back. What kind of predatory dinosaur looked like this? It defied everything paleontologists thought they understood about large carnivores. Stromer named it Spinosaurus aegyptiacus, the Egyptian spine lizard. But here's the tragic part of this story. Those precious fossils, carefully excavated, studied, and housed in the Paläontologisches Museum München in Germany, were destroyed in 1944 during an Allied bombing raid on Munich. In one terrible night, the only substantial remains of one of the most bizarre dinosaurs ever discovered were reduced to rubble and dust. If you're finding these stories of discovery, loss, and rediscovery as fascinating as I do, I'd appreciate it if you'd like this video and subscribe. The journey of understanding Spinosaurus spans over a century, and involves some of the most dramatic revelations in paleontology. For decades after those fossils were destroyed, Spinosaurus existed only in drawings and scientific descriptions. It was a ghost dinosaur, known but unknowable, its true nature lost to history. Paleontologists could only speculate about what this creature had been like, working from Stromer's notes and a few photographs that survived the war. And speculate they did. Was it a giant predator like Tyrannosaurus rex, but with a sail? Was it a scavenger? How did it move? What did it eat? Then, beginning in the early 2000s, new fossils started to emerge. Fragmentary at first, a tooth here, a partial skull there, but each piece added to our understanding. And then came the breakthrough that would revolutionize everything we thought we knew about Spinosaurus. In 2014, a team led by paleontologist Nizar Ibrahim published a study that shocked the scientific world. They had found and analyzed new Spinosaurus material from Morocco, and what they discovered suggested something almost unthinkable. This wasn't just a predator that lived near water. Spinosaurus appeared to be adapted for a semi-aquatic lifestyle, spending significant time actually in the water, hunting aquatic prey. This would make it the first known semi-aquatic dinosaur, a category paleontologists didn't even think existed. Let me walk you through why this was so revolutionary. Everything we knew about large theropod dinosaurs, the group that includes Tyrannosaurus, Allosaurus, and all the other big predators, suggested they were terrestrial hunters. Yes, some might wade into shallow water occasionally, just as lions will cross rivers. But a dinosaur actually adapted to swim, to spend extended periods submerged, actively hunting in an aquatic environment. That challenged fundamental assumptions about dinosaur biology and behavior. The evidence, however, was compelling. Let's start with the most visible feature, that enormous sail. In Spinosaurus, the neural spines extending from the vertebrae could reach heights of 5.5 feet. Covered in life by skin, blood vessels, and possibly a layer of fat, this would have created a structure measuring perhaps 7 feet tall, running down much of the animal's back. For context, that's taller than most humans. What could such a structure possibly be for? Scientists have proposed several hypotheses, and understanding these theories teaches us something important about how paleontologists think through these puzzles. The first hypothesis is thermoregulation, temperature control. Imagine you're a massive predator living in a hot climate. Your body generates heat through metabolism, and that enormous mass means heat dissipates slowly. This is actually a problem for large animals in warm environments. Elephants deal with it by having large ears filled with blood vessels. As air moves past their ears, it cools the blood, which then circulates back through the body. Could Spinosaurus's sail serve a similar function? A large, thin structure filled with blood vessels would provide enormous surface area for heat exchange. In the morning, the animal could orient the sail toward the sun, warming its blood and raising its body temperature. During the heat of the day, it could move to shade or water, using the sail to dissipate excess heat. It's an elegant solution, and it's similar to what we see in some modern sailfin lizards. But there's a compelling alternative: sexual display. In nature, some of the most elaborate structures organisms possess aren't for survival at all. They're for reproduction. Think of a peacock's tail, the antlers of a male deer, or the elaborate bower constructions of certain bird species. These features are costly to maintain, sometimes even detrimental to survival. But if they help an animal attract mates and pass on its genes, evolution favors them. Could Spinosaurus's sail have been a display structure? Perhaps it was brightly colored or patterned in ways that signaled genetic fitness to potential mates. Maybe males had larger, more elaborate sails than females, and they would display them during mating season, showing off their size and health. We see this pattern in many modern animals, where sexual selection drives the evolution of spectacular but seemingly impractical features. There's also a third possibility, less discussed but worth considering. fat, and energy storage. Some scientists have proposed that the sail could have been covered with a fatty hump, similar to what we see in modern camels or bison. This would provide energy reserves during times when food was scarce. In an environment with seasonal variations in prey availability, such reserves would be valuable. The truth might involve a combination of these functions. Evolution is remarkably efficient at making structures serve multiple purposes. The sail could have helped with temperature regulation, while also serving as a display feature. It might have stored fat reserves while simultaneously making the animal appear larger and more impressive to rivals or potential threats. But the sail, as distinctive as it is, isn't the most surprising thing about Spinosaurus. That honor goes to the mounting evidence that this dinosaur was semi-aquatic. Let's examine this evidence piece by piece, because it's absolutely fascinating how scientists put this puzzle together. First, consider the skull. When you compare Spinosaurus's skull to other large theropods, the difference is striking. Tyrannosaurus rex had a deep, powerful skull filled with thick, serrated teeth, designed to crush bone and tear flesh. Spinosaurus's skull was long and narrow, almost delicate by comparison, with conical teeth. If you didn't know it was a dinosaur and just looked at the skull, you might think it belonged to a crocodilian. In fact, it's remarkably similar to the skull of a modern gharial, a fish-eating crocodilian from India. This convergent evolution, where unrelated animals develop similar features because they're solving similar problems, is a powerful clue. Gharials have long, narrow snouts because this shape is ideal for sweeping through water to catch fish. The slender profile reduces drag, and the conical teeth are perfect for gripping slippery prey without tearing chunks out of it. If Spinosaurus had a similar skull, might it have been doing similar things? The teeth themselves tell a story. When paleontologists examine wear patterns on Spinosaurus teeth, they see evidence consistent with a diet of fish and other aquatic prey. Moreover, fossil sites that contain Spinosaurus remains are rich in fish fossils and other aquatic creatures. One specimen even had fish scales preserved near its gut region, direct evidence of its last meal. But perhaps the most convincing evidence comes from the skeleton itself, particularly discoveries made in the last decade. The 2014 study revealed that Spinosaurus had remarkably dense bones, much denser than typical theropods. This is called osteosclerosis, and it's a feature we see in many aquatic animals. Why would dense bones be advantageous for a swimmer? Think about buoyancy. Animals that spend time in water face a challenge. Air-filled lungs and light bones make them float. This is fine for animals that swim at the surface, but for those that need to dive or swim underwater, it's a problem. Dense bones act as natural ballast, helping the animal maintain neutral buoyancy or sink when needed. Modern aquatic mammals like hippos and manatees have dense bones. So do penguins. When paleontologists examined Spinosaurus's bone density and compared it to other dinosaurs and to modern animals, they found it fell into the range typical of semi-aquatic creatures. This wasn't a dinosaur that occasionally waded in shallow water. This was an animal built to spend significant time submerged. Then, in 2020, came perhaps the most dramatic revelation of all. Another team published findings about Spinosaurus's tail. They had discovered tail vertebrae that, when reconstructed, showed something unprecedented. The tail was tall and laterally compressed, flattened from side to side, with elongated neural and chevron spines creating a fin-like structure. Computer simulations and physical models demonstrated that this tail would have been an effective swimming organ, capable of generating thrust through lateral undulation, just like a crocodile's tail or a newt's tail. Can you imagine what this means? This wasn't speculation or inference. This was direct evidence that Spinosaurus had a propulsive swimming tail. No other dinosaur has ever been found with such an adaptation. It's as if evolution decided to take a giant predatory dinosaur and reimagine it as an aquatic hunter. let's paint a picture of what life might have been like for Spinosaurus. We're in North Africa during the mid-Cretaceous period, about 95 million years ago. The world is warmer than today. There are no ice caps at the poles. Sea levels are high. What is now the Sahara Desert was then a vast river system, teeming with life. Rivers and estuaries created a complex aquatic ecosystem filled with enormous fish, some as large as cars, along with crocodilians, turtles, and other aquatic reptiles. Into this environment comes Spinosaurus. It's enormous. Estimates suggest it could reach 50 feet in length, possibly longer, making it one of the largest predatory dinosaurs ever discovered, potentially rivaling or exceeding Tyrannosaurus rex in size. But unlike T-Rex, which hunted on land, Spinosaurus has adapted to a different niche. Picture the animal wading into the river, its powerful hind legs pushing through the water. The sail on its back rises above the surface like the fin of some primordial shark. As it moves into deeper water, the animal begins to swim, its long tail sweeping back and forth, providing thrust. The dense bones prevent it from being too buoyant. It can submerge partially, its eyes and nostrils positioned on top of its skull, allowing it to see and breathe while mostly underwater. Another adaptation similar to crocodilians. Below the surface, schools of large fish move through the murky water. Spinosaurus's eyes spot movement. Those powerful jaws, filled with conical teeth, snap sideways in a motion more like a crocodile than a typical dinosaur. The teeth interlock around a struggling sawfish. The prey is hauled to shallower water or onto a bank, where it can be consumed at leisure. This is a lifestyle unlike any other dinosaur we know of. While its relatives like Carcharodontosaurus, a massive land predator whose fossils are found in the same formations, hunted sauropods and other large dinosaurs on land, Spinosaurus exploited the rich aquatic resources that other predators largely ignored. But here's what's truly fascinating. Spinosaurus probably wasn't exclusively aquatic. The structure of its hind legs, while unusual, still suggests it could walk on land. It likely nested on land, as all dinosaurs apparently did. Young Spinosaurus would have hatched from eggs in nests built on riverbanks or in coastal areas, just like modern crocodiles. The animal probably spent time basking on shores, using that enormous sail to regulate its body temperature. What we're seeing in Spinosaurus is an animal in transition, evolutionarily speaking. It's not fully aquatic like a whale or ichthyosaur, those marine reptiles that were contemporaries of the dinosaurs, but were completely adapted to ocean life. Spinosaurus still retained the basic terrestrial dinosaur body plan, but modified it significantly for a semi-aquatic lifestyle. It's an intermediate form, a snapshot of evolution in action. This brings us to an important comparison: Dimetrodon. If you've ever seen a picture of Dimetrodon in a book about dinosaurs, there's something I need to tell you. Dimetrodon wasn't a dinosaur at all. It lived about 280 million years ago, during the Permian period, long before dinosaurs evolved. It was a synapsid, more closely related to mammals than to dinosaurs. But Dimetrodon had a sail remarkably similar to Spinosaurus's sail. Here we have two completely unrelated animals, separated by about 200 million years of evolution, living in different eras, belonging to different branches of the vertebrate family tree, and yet both evolved prominent back sails. This is convergent evolution in action, when similar environmental pressures or lifestyles lead unrelated organisms to develop similar features. In Dimetrodon's case, the sail likely serves similar purposes to what we've discussed for Spinosaurus: thermoregulation, display, possibly both. But the fact that two such different animals independently evolve similar structures tells us something important. It suggests that a large sail on the back is a viable evolutionary solution to certain problems or opportunities. It's not just a weird one-off quirk, but a design that nature has returned to multiple times across vast stretches of time. the story of Spinosaurus is still being written. Every few years, new discoveries refine our understanding. There are still debates in the scientific community about exactly how aquatic Spinosaurus was, whether it actively swam or mostly waded, whether it could catch fish in open water or primarily ambush them in shallows. These debates are healthy. They represent science at its best, with researchers examining evidence, running experiments, building models, and gradually converging on truth. What's not debatable is that Spinosaurus represents one of the most bizarre and specialized dinosaurs ever discovered. It shows us that dinosaurs were far more diverse than we often imagine, capable of adapting to ecological niches we wouldn't expect them to occupy. It reminds us that the age of dinosaurs wasn't just about giant predators roaming the land and peaceful herbivores browsing in forests. It was far stranger, far more complex, far more wonderful than that simple picture. The loss of the original fossils in 1944 was a tragedy for science. How much more might we have learned if those specimens still existed? But in a way, the story of Spinosaurus is also a story of scientific resilience. The knowledge wasn't permanently lost. New discoveries, new specimens, new technologies all came together to bring this creature back from obscurity, to help us understand not just that it existed, but how it lived. And as we've seen with both Iguanodon and Spinosaurus, paleontology is a science of constant revision and refinement. What we know about dinosaurs today will undoubtedly be updated, corrected, and expanded by future discoveries. That's not a weakness, it's a strength. It means our understanding is always growing, always improving, always approaching closer to the truth. The aquatic adaptations of Spinosaurus represent one extreme of dinosaur diversity, but evolution explored other extremes as well. Some of the strangest dinosaurs weren't adapted for unusual environments or diets. They were equipped with features that seemed designed primarily for combat. Features so robust, so powerful, that they invite us to imagine dinosaurs engaging in behaviors that would be spectacular, even frightening to witness. Our next creatures possess skulls transformed into weapons, domes of bone thick enough to survive impacts that would shatter concrete. The headbutters are waiting to tell their story. Imagine two massive animals, each weighing close to 1,000 pounds, charging at each other at speeds approaching 15 miles per hour. Their heads collide with a crack that echoes through the forest. The impact generates forces equivalent to a small car crash. But neither animal falls, neither suffers a concussion or broken skull. Instead, they back away, reassess, and prepare to charge again. This isn't a scene from a monster movie. This might have been a regular occurrence in the forests of late Cretaceous North America, some 66 to 70 million years ago. The creatures engaging in this spectacular display were pachycephalosaurs, and their skulls were unlike anything else in the dinosaur world. The dome on top of a Pachycephalosaurus skull could measure up to 10 inches thick. That's about 25 centimeters of solid bone. To put that in perspective, that's roughly the thickness of a hardcover encyclopedia. Now imagine that encyclopedia is made entirely of bone, and it's mounted on top of a dinosaur's head. That's the reality of these remarkable creatures. But here's the question that has divided paleontologists for decades. Were these dome skulls actually used for headbutting combat? Or were they primarily for display? The answer isn't as simple as you might think, and the debate teaches us fascinating lessons about how we interpret ancient behavior from fossilized remains. If you're intrigued by these mysteries of dinosaur behavior and biomechanics, I'd be grateful if you'd take a moment to like this video and subscribe. These debates in paleontology show us how science grapples with questions that can never be directly observed, only carefully inferred from evidence. The story of Pachycephalosaurs begins with partial remains discovered in the late 1800s, but it wasn't until 1943 that we got our first good look at what these animals really were. That year, paleontologist Barnum Brown and his colleague Eric Marin Schleicher described Pachycephalosaurus wyomingensis based on a skull found in Montana. The name means thick-headed lizard from Wyoming, which is perhaps the most straightforward dinosaur name ever given. When you look at a Pachycephalosaurus skull for the first time, it's striking. The dome rises from the head like a biological helmet, smooth and rounded. Around the base of the dome and along the snout are bony knobs and spikes, giving the head an almost crown-like appearance. The whole structure looks purpose-built for impact, which is why the head-butting hypothesis has been so persistent and popular. Let's examine this hypothesis carefully, because it requires us to think through the biomechanics of what would happen if these animals really did bash their heads together. First, consider the skull itself. That dome of bone is composed of dense, compact bone with a unique structure. When researchers examine thin sections of Pachycephalosaur domes under microscopes, they find that the bone has a particular orientation and density that would help dissipate impact forces. The fibers are arranged in patterns that redirect stress away from critical areas. It's sophisticated engineering, the kind of structure you'd want if you were designing something to withstand repeated impacts. But the skull is only part of the story. If these animals were headbutting, they'd need more than just a thick skull to survive. They'd need a whole suite of adaptations throughout their skeleton to handle the enormous forces involved. Let's think about what happens during an impact. When two objects collide, force travels through them. If you've ever hit your thumb with a hammer, you understand this intuitively. The impact point might hurt, but you also feel the shock traveling up your arm. Now scale that up to two massive dinosaurs colliding at speed. The force doesn't just stop at the skull, it travels down the neck, into the spine, through the hips, and into the legs. This is where things get really interesting. When paleontologists examined the neck vertebrae of Pachycephalosaurus, they found something remarkable. The vertebrae are tightly interlocking, with specialized joints that limit side-to-side movement, while allowing the neck to flex forward and backward. The neural spines, those projections from the top of each vertebra, are robust and well-developed, providing attachment points for powerful muscles and ligaments. This is exactly what you'd expect if the animal needed to keep its head, neck, and body in a rigid line during impact. Think of it like a spear. A spear works because all its parts are aligned. The shaft, the point, everything in a straight line, so force transfers efficiently. If a spear bent or twisted during impact, it would fail. Similarly, for headbutting to work, Pachycephalosaurus would need its entire body aligned during collision. And indeed, when researchers reconstructed the animal's posture, they found that it could hold its head, neck, back, and tail in a nearly straight horizontal line. The tail was stiffened by ossified tendons, strands of tendon that had turned to bone, creating a rigid support structure. This horizontal posture would be ideal for absorbing and distributing impact forces during head-to-head collisions. The hips and legs also show interesting features. They're robust, built for power rather than speed. The feet are relatively large with well-developed joints, perfect for maintaining balance and traction during impact. All of these features are consistent with an animal built to withstand significant collision forces. So far, the evidence seems to support headbutting, doesn't it? But this is where science gets interesting, because there's compelling evidence on the other side of the debate as well. Critics of the headbutting hypothesis point out several problems. First, let's talk about the shape of the dome itself. In most Pachycephalosaur specimens, the dome is smoothly rounded. While this distributes force well, it also means that during a head-on collision, the domes would tend to glance off each other rather than making solid contact. Imagine trying to push two bowling balls together. They slide off to the sides rather than staying in contact. For effective headbutting, you might expect to see flatter impact surfaces, like we see in modern bighorn sheep. Speaking of bighorn sheep, let's look at what modern headbutters actually do. Bighorn sheep are famous for their spectacular head-clashing battles during mating season, but watch carefully how they fight. They don't run full speed at each other from a great distance. They typically start relatively close, rear up, and then bring their heads together with a shorter charge. Their horns are curved and rough-textured, with surfaces that grip during impact rather than sliding off. Their entire combat behavior is evolved to make effective contact and minimize the chance of neck injuries. Could pachycephalosaurs have engaged in similar behavior? Perhaps. But here's another complication: the angle of impact. For headbutting to work without causing severe neck injuries, the angle of impact needs to be relatively straight on, with the force traveling directly down the spine. If the heads collide at an angle, twisting forces are generated that could seriously damage the neck vertebrae. Some researchers have conducted computer simulations and physical models testing different collision scenarios. These studies suggest that while the pachycephalosaur skull could withstand direct impacts, the neck might be vulnerable to injury if impacts occurred at even slightly wrong angles. And in the chaos of two animals charging at each other, perfect alignment seems difficult to guarantee. There's also the question of injuries. If pachycephalosaurs regularly engage in violent headbutting contests, we might expect to see evidence of this in the fossils. Fractured domes, damaged vertebrae, signs of repeated trauma. While some pachycephalosaur skulls do show pathologies, areas where bone has been damaged and healed, these aren't as common as we might expect if headbutting was a regular occurrence. And many of the pathologies that are present could be explained by other causes, such as infections or accidents rather than combat. This brings us to the alternative hypothesis: display. What if those massive domes weren't primarily weapons, but rather visual signals? In the animal kingdom, many features that appear to be weapons are actually used more for show than for fighting. Male deer have impressive antlers, but most of their competition with other males involves displaying those antlers, posturing, and vocalizing. Actual combat is relatively rare and usually brief. Could pachycephalosaur domes have served a similar function? Imagine a male Pachycephalosaurus during mating season. His dome is large and impressive, possibly covered with brightly colored or patterned skin. He displays it to rivals and potential mates, showing off his size and health. Most conflicts are resolved through these visual displays. Only occasionally, when display isn't enough, does physical contact occur. And even then, it might be less violent than full-speed head-on collisions. This display hypothesis is appealing, but it doesn't necessarily mean headbutting never occurred. In nature, features often serve multiple functions. A deer's antlers are used for display most of the time, but they can also be used in actual combat when necessary. Perhaps pachycephalosaur domes were similar, primarily for display, but capable of withstanding impacts when needed. There's another fascinating aspect to the pachycephalosaur story, one that relates to how we classify and understand these animals. For years, paleontologists recognized several different species of dome-headed dinosaurs from the same time and place. There was Pachycephalosaurus, of course, the giant with the massive dome. But there were also smaller species like Stygimoloch, which had a smaller dome covered with impressive spikes, and Dracorex, which had an almost flat skull decorated with elaborate horns and knobs. These were described as separate species, each with its own scientific name, each presumably representing a different branch on the Pachycephalosaur family tree. Dracorex even got one of the coolest scientific names in paleontology: Dracorex hogwartsia, the Dragon King of Hogwarts, named by a group that included young paleontology enthusiasts. But then researchers noticed something interesting. All of these different species were found in the same rock formations from the same time period. They all had similar body proportions apart from their heads. And when paleontologists started examining the microscopic structure of the skull bones, they found evidence that some of these supposedly different species might not be different species at all. The bone structure suggested that specimens of Stygimoloch and Dracorex were juveniles or subadults, not fully grown. As these animals matured, their skulls would have changed dramatically. The spikes would have been reabsorbed into the growing dome. The flat or slightly domed skull would have developed into the high, rounded dome of adult Pachycephalosaurus. This is called ontogenetic variation, changes that occur as an organism grows from juvenile to adult. It's common in nature. Human babies look different from adults, not just smaller, but with different proportions, a relatively larger head, and so on. Many animals show even more dramatic changes. The larva of a butterfly looks nothing like the adult butterfly. If this hypothesis is correct, and not all paleontologists agree, which is healthy scientific debate, it means that what we thought were 3 separate species were actually just different growth stages of the same animal. It would be like if an alien paleontologist found fossils of human children and human adults and, not understanding that they were the same species at different ages, classified them as 2 separate species of hominid. This teaches us something crucial about how we interpret the fossil record. We're not just looking at static specimens. These were living creatures that grew, changed, and developed over their lifetimes. Understanding this developmental context is essential for accurate classification and for understanding how these animals lived. It also relates back to our head-butting debate. If Dracorex and Stygimoloch are indeed juvenile Pachycephalosaurus, it suggests that the dome developed as the animals matured. This would make sense if the dome was related to adult behaviors like mating competition. Young animals wouldn't need massive combat-ready skulls. They'd develop those features as they reached sexual maturity and needed to compete for mates. This pattern is common in animals where males compete for mating opportunities. Young males don't have the full-sized weapons or ornaments of adults. They develop them as they mature, right around the time they start competing for reproductive success. If Pachycephalosaurs followed this pattern, it's another piece of evidence that those domes had something to do with intraspecific competition between members of the same species. Whether that competition involved actual headbutting combat, ritualized pushing contests, or primarily display behavior remains an open question. Perhaps the answer is all of the above. Maybe young Pachycephalosaurs, with their smaller, flatter skulls, engaged primarily in display and occasional light sparring. As they matured and their domes developed, perhaps more serious head-pushing or head-butting contests became possible and more common. The truth is, we may never know with absolute certainty how these animals use their remarkable skulls. We can't observe their behavior directly. We can't watch them interact during mating season. All we have are bones, and while bones can tell us a great deal, behavior rarely fossilizes. But this uncertainty isn't a failure of science. It's an opportunity. It reminds us that our understanding is always provisional, always open to revision as new evidence emerges. Maybe someone will discover new fossils with clearer injury patterns. Perhaps more detailed biomechanical modeling will settle the debate. Or maybe we'll find fossilized trackways showing Pachycephalosaurs in action, giving us direct evidence of their behavior. What we do know is that Pachycephalosaurs were successful animals. They lived for millions of years, spread across multiple continents, and filled an ecological role in their ecosystems. Those elaborate skulls, whatever their primary function, clearly provided some evolutionary advantage. They weren't a failed experiment or an evolutionary dead end. They were a successful adaptation that worked for the creatures that possessed them. And isn't there something wonderful about that uncertainty? About knowing that despite all our technology, all our scientific methods, all our careful study, there are still mysteries? The past still holds secrets. And perhaps some of those secrets will remain forever, just beyond our reach, inviting us to wonder and speculate and imagine. The dome-headed Pachycephalosaurs show us one way evolution can modify a skull for specialized purposes. But what if evolution didn't modify the skull for combat or display? What if instead it modified the hands? We've already met Iguanodon with its thumb spike. But there's another group of dinosaurs that took hand modification to an almost absurd extreme, developing claws so enormous they seem to defy explanation. These were herbivores carrying weapons that could eviscerate a predator, gentle giants equipped with what looked like slashing tools from a nightmare. The Therizinosaurs are about to challenge everything we think we know about how herbivorous dinosaurs should be built. In 1948, a Soviet-Mongolian paleontological expedition was working in the Gobi Desert when they uncovered something that defied explanation. Enormous claws. Not just large, truly massive, measuring nearly 3 feet in length along their outer curve. They were unlike anything anyone had seen before. The structure suggested they belonged to some kind of theropod dinosaur, the group that includes all the famous predators like Tyrannosaurus and Velociraptor. But claws this size on a predator? What could such a creature possibly have hunted? What prey would require weapons of such incredible proportions? The expedition leader initially thought they might belong to a giant turtle, a reasonable guess given their curved shape. Others speculated about a massive carnivore, perhaps the apex predator of its ecosystem. The fossils were given a name that reflected their mysterious nature, Therizinosaurus, meaning scythe lizard. For decades, these claws remained one of paleontology's greatest puzzles. What kind of animal possessed them? How did it live? What were these extraordinary structures used for? The answer, when it finally came through additional discoveries in the 1990s and 2000s, was so unexpected that it forced paleontologists to completely rethink their assumptions about dinosaur evolution. Because those fearsome-looking claws, those weapons that seem designed for slaughter, belong to a plant eater, a gentle herbivore. And that paradox is where our story truly begins. If you're finding these paradoxes of evolution as fascinating as I do, I'd appreciate if you'd consider liking and subscribing. Each of these strange creatures teaches us something profound about how life adapts to challenges in ways we might never predict. Let's start by understanding what makes Therizinosaurs so profoundly strange. We need to build a complete picture of these animals because the claws, dramatic as they are just one piece of an overall body plan that seems almost comically mismatched. Picture, if you will, an animal standing about 16 feet tall when it rears up. It has a relatively small head on the end of a long, graceful neck, not quite as long as a sauropod's neck, but long enough to reach high into trees. The body is bulky and pot-bellied, giving the animal a somewhat ungainly appearance. The legs are thick and powerful, but built more like a bird's than a typical dinosaur's, with the thighs held relatively horizontal and the lower legs extending downward. And then there are those claws. On each hand, 3 massive curved claws that could measure up to 3 feet long, extending from relatively short arms. It's a body plan that looks like it was assembled from spare parts of different animals. The neck of a sauropod, the body of a hadrosaur, the legs of a large bird, and the claws of, well, nothing else in nature quite compares to those claws. When paleontologists first began finding more complete Therizinosaurus fossils in the late 20th century, piecing together what these animals actually were, the discoveries challenged fundamental assumptions about theropod dinosaurs. Remember, theropods are the group that includes all the famous carnivores. Tyrannosaurus, Allosaurus, Velociraptor. They're all theropods. The defining characteristics of this group include features that evolved for hunting: sharp teeth, powerful jaws, grasping hands with claws, and a body built for pursuing prey. Therizinosaurs had the basic theropod body plan, but they had modified it so dramatically that they barely resembled their carnivorous cousins anymore. And here's what's truly remarkable. This wasn't a one-time evolutionary accident. The Therizinosaur family included multiple species spanning millions of years, all following this same bizarre pattern. Evolution had taken a group of meat eaters and transformed them into plant eaters, but it hadn't given them the body of typical herbivores. Instead, It kept modifying the predator template, creating something entirely new. To understand why this is so significant, we need to talk about evolutionary constraint. When a lineage of organisms evolves, it doesn't start from scratch. Evolution can't design a perfect organism for every environment. Instead, it works with what's already there, modifying existing structures. It's like renovating a house. You work within the constraints of the existing foundation, walls, and structure. You can make dramatic changes, but you're always building on what came before. Therizinosaurs show us this process in action. They descended from carnivorous theropods, and their skeleton still reflects that ancestry. But as they shifted to an herbivorous diet, natural selection modified their features to suit this new lifestyle. The result is an animal that doesn't look like a typical herbivore because it wasn't built from an herbivore blueprint. It was built by modifying a predator. Now, let's focus on those extraordinary claws because they're central to understanding these animals. When you examine a Therizinosaurus claw, and you can see casts in various museums around the world, several things become apparent. First, the sheer size. These aren't just long, they're robust, with a thick cross-section that speaks to incredible strength. Second, the curve. They sweep in a gentle arc, not a tight hook like a cat's claw, but a broader curve. Third, the edges. Unlike the claws of predators, which are often sharp along their inner edge for gripping prey, Therizinosaurus claws are relatively blunt. These structural details give us clues about function, but interpreting them requires careful thought. Let's consider the main hypotheses about what these claws were used for. The first and most obvious idea is that they were defensive weapons. An herbivore living in a world with large predators would benefit from effective defense mechanisms. And there's no question that a therizinosaur could be dangerous if threatened. Imagine you're a Tarbosaurus, the Asian cousin of Tyrannosaurus rex, and you decide to attack what looks like an easy meal, a pot-bellied plant eater. But as you close in, this herbivore rears up on its hind legs, suddenly standing taller than you, and brings down those enormous claws in a slashing motion. Those claws, driven by powerful arm muscles and the weight of a 5-ton animal, could inflict devastating wounds. We can look at modern animals for comparison. Sloths, despite being peaceful herbivores, have substantial claws that they can use quite effectively in defense when threatened. Therizinosaurs would be like sloths scaled up by a factor of 20 or 30, with proportionally even larger claws. Any predator would think twice before attacking such a well-armed herbivore. But here's the challenge with the defense hypothesis. Those claws might be too valuable for defense alone to explain their evolution. Think about the cost of maintaining such enormous structures. The claws themselves are made of bone at the core, covered with a keratin sheath. Growing and maintaining them requires significant metabolic energy and nutrients. They add weight that the animal must carry around constantly. If they were used frequently in combat, they'd risk damage. A broken claw would be a serious problem for the animal. In nature, purely defensive structures tend to be as small and efficient as possible while still being effective. Therizinosaur claws seem to go beyond what's necessary for defense, which suggests they might have had additional functions. This brings us to the feeding hypothesis. What if these claws were primarily tools for accessing food? Consider the environment where Therizinosaurs lived. We're talking about the Cretaceous period, roughly 70 to 90 million years ago, in what is now Mongolia and China. This was a world of varied vegetation, conifers, cycads, and increasingly flowering plants, which were diversifying rapidly during this period. For an herbivore, accessing as much food as possible is crucial. Competition with other herbivores means that any advantage in reaching different food sources translates to better nutrition, better health, and ultimately, more successful reproduction. Those long claws could function as hooks for pulling down high branches that other herbivores couldn't reach. The long neck would let the animal reach upward, the claws would hook around branches, and the powerful arms would pull them down to mouth level. Think about how a giraffe feeds. It uses its height and long tongue to access acacia leaves that other animals can't reach. Therizinosaurs might have used a similar strategy, but with the addition of those claws as tools. This would give them access to a food source that was underutilized by other herbivores in their ecosystem. High vegetation that required both reach and the ability to pull branches within range. There's also the possibility that the claws were used for stripping bark or digging into termite mounds. Some modern animals, like giant anteaters, have substantial claws that they use to break into insect nests. While we have no direct evidence that therizinosaurs ate insects, it's not impossible that they supplemented their primarily herbivorous diet with protein-rich insects when available, using those claws to access colonial insects like termites. But there's a third hypothesis we need to consider, one that's less dramatic, but might be equally important: sexual selection and display. In many species, features that seem impractical or exaggerated evolved not for survival, but for reproduction. They're signals of genetic fitness, advertisements to potential mates. Consider the peacock's tail. It's enormous, heavy, brightly colored, and makes the bird more visible to predators. By any practical measure, it's a handicap. But it exists because peahens prefer males with impressive tails. The tail signals that the male has good genes. He's healthy enough, strong enough, skilled enough at finding food and avoiding predators that he can afford to carry around this elaborate ornament. It's what biologists call an honest signal of fitness. Could therizinosaur claws have served a similar function? Perhaps individuals with larger, more impressive claws were more successful at attracting mates. During mating season, males might have displayed their claws, showing off their size and symmetry. Fights between rivals might have involved claw displays and ritualized combat that rarely resulted in serious injury, but allowed individuals to assess each other's size and strength. This doesn't mean the claws couldn't also be used for feeding or defense. In nature, structures often serve multiple purposes. A deer's antlers are primarily for mating competition. Males with larger antlers tend to win more contests and attract more mates. But those same antlers can also be used for defense against predators or for stripping bark from trees. Multiple functions can drive the evolution of a single structure. What makes therizinosaurs even more fascinating is their evolutionary history. How did descendants of carnivorous theropods end up as pot-bellied herbivores with giant claws? This shift from meat-eating to plant-eating is relatively rare in dinosaur evolution, but it did happen several times, and each instance teaches us something about how evolution works. The transition probably happened gradually, over many millions of years and multiple species. The ancestors of therizinosaurs were likely small carnivorous dinosaurs, perhaps similar to early coelurosaurs from the Jurassic period. These were agile predators with sharp teeth and grasping claws, hunting small prey in Mesozoic forests. At some point, perhaps during a period of environmental change or increased competition with other predators, some of these dinosaurs began supplementing their diet with plants. This isn't unusual. Many modern carnivores occasionally eat plant material. Bears, for example, are technically carnivores, but many species eat substantial amounts of vegetation, from berries to bamboo. As these proto-therizinosaurs incorporated more plant material into their diet, natural selection began favoring features that made herbivory more efficient. Perhaps their teeth became less sharp, better for grinding than tearing. Their jaw muscles might have changed to provide better chewing motion. Their digestive systems would have needed to adapt to break down tough plant cellulose, possibly becoming longer and more complex, which would explain that characteristic potbelly. It's housing an elaborate fermentation chamber for digesting plants. With each generation, individuals who were better adapted to an herbivorous lifestyle would have had advantages. They could access food sources their carnivorous competitors ignored. They faced less competition for prey. Over time, the population shifted further and further toward herbivory, until they became specialized plant eaters who had almost entirely abandoned their predatory ancestry. But they never lost their theropod body plan entirely. Those claws, inherited from grasping predators, were repurposed for new functions. The long arms, once for grabbing prey, became tools for reaching and pulling vegetation. The sharp teeth were lost, replaced with smaller leaf-shaped teeth, suitable for cropping plant material. But the basic skeletal structure, the hip arrangement, the leg proportions, these still mark them as theropods. This evolutionary path is called adaptive radiation, where a lineage diversifies to fill new ecological niches. But it's a specific type, a transition from one dietary strategy to another. It shows us that evolution is opportunistic. It doesn't plan ahead. It doesn't say, we're going to become herbivores, so we need to evolve an herbivore body plan. Instead, it works with what's available, making incremental changes that provide immediate benefits. Have you ever wondered why evolution sometimes creates solutions that seem inefficient or overly complicated? The answer is historical contingency. Evolution can only work with existing variation. It can't go back to the drawing board and start fresh. Therizinosaurs show us this principle beautifully. They're herbivores, but they're built on a carnivore chassis, resulting in a body plan that seems odd to us but worked perfectly well for them. And work it did. Therizinosaurs were successful, surviving for millions of years across multiple continents. Fossils have been found in Asia and North America, suggesting they were widespread and well adapted to their environments. They lived alongside other famous dinosaurs, hadrosaurids, ceratopsians, and large predators like Tarbosaurus, and held their own in these competitive ecosystems. Different Therizinosaurus species show interesting variations on the basic theme. Nothronicus, found in North America, had somewhat shorter claws, but a similar body plan. Bepiaosaurus, from China, is one of the earliest known therizinosaurs and shows features intermediate between carnivorous theropods and later, more specialized forms. It still had relatively sharp teeth compared to later species. Erlikosaurus had a particularly unusual skull structure, adapted for specialized feeding. Each species represents evolution, experimenting with different variations within the therizinosaur blueprint. The discovery and gradual understanding of therizinosaurs is a wonderful example of how paleontology progresses. From those first mysterious claws in 1948, it took decades to piece together what these animals were. Each new fossil added information. Each discovery answered some questions while raising new ones. Gradually, through the work of researchers across multiple countries and decades, a coherent picture emerged. This process teaches us patience and humility in science. The first scientists who found those enormous claws made reasonable guesses based on the evidence available to them. A giant predator, a massive turtle. They were wrong, but not because they were bad scientists. They were making the best inferences possible with incomplete data. As more evidence accumulated, the true nature of therizinosaurs became clear. This is how science is supposed to work, forming hypotheses, testing them against new evidence, revising when necessary. It also reminds us not to make assumptions based on what seems normal. A plant-eating theropod with meter-long claws doesn't fit our expectations of how herbivores should look. But nature doesn't care about our expectations. Evolution explores whatever possibilities work, however strange they might seem to us. The therizinosaurs represent one of evolution's most creative experiments, taking predators and transforming them into herbivores, but doing so in a way that created something entirely unique. Those magnificent claws, whether they were primarily for feeding, defense, display, or most likely some combination of all three, stand as testament to the remarkable creativity of natural selection. While therizinosaurs show us bizarre modifications to the hands and feeding apparatus, there were other dinosaurs that took a completely different approach to herbivore design. Instead of relying on claws or specialized feeding structures, they invested in defense, comprehensive, elaborate defense that turned them into living fortresses. These armored dinosaurs didn't try to reach food that others couldn't, and they didn't try to run from predators. They had a different strategy entirely. They made themselves so difficult to attack that predators would choose easier prey. And some of them possessed a weapon so powerful, so precisely engineered, that one blow could shatter bones. The story of the armored tanks with tail clubs awaits. Imagine standing in a late Cretaceous forest about 68 million years ago in what would one day become Montana. Through the vegetation, you spot movement. A massive, low-slung creature browsing on ferns and low-growing plants. At first glance, it appears peaceful, almost sluggish. But then you notice the details. The entire upper surface of its body is covered in thick, bony plates, each one embedded in the skin like natural armor. Rows of spikes project from its flanks, and at the end of its tail, suspended by specialized vertebrae, hangs a massive club of fused bone, a weapon that, when swung with the full force of this multi-ton animal's muscle power, could deliver a blow capable of shattering the leg bone of a Tyrannosaurus rex. This is Ankylosaurus, and it represents one of evolution's most impressive achievements in defensive engineering. But the story of how paleontologists came to understand this remarkable creature, and how modern science has tested the devastating power of that tail club, reveals truths about evolution, biomechanics, and the ancient arms race between predators and prey that shaped the Mesozoic world. If these explorations of evolutionary engineering fascinate you as much as they do me, I'd be grateful if you'd take a moment to like this video and subscribe. Understanding how these ancient defense systems worked requires us to think like engineers, biologists, and physicists all at once. The first Ankylosaurus fossils were discovered in 1906 in the Hell Creek Formation of Montana by legendary fossil hunter Barnum Brown, the same man who would later discover Tyrannosaurus rex. Brown recognized immediately that this was something extraordinary, a dinosaur that seemed to have evolved comprehensive body armor. He named it Ankylosaurus magniventris, meaning fused lizard with great belly, a reference to both the fused armor plates and the wide barrel-shaped body. But here's what's remarkable about the early history of Ankylosaurus study. For decades, paleontologists had only fragmentary remains to work with. A skull here, some armor plates there, occasionally a tail club, but rarely complete skeletons. It wasn't until much later, with discoveries in the 1990s and 2000s, that scientists could fully appreciate how these animals were constructed. And what they found was astonishing. Ankylosaurus wasn't just armored, it was a masterpiece of defensive design, with multiple systems working together to make it one of the most difficult prey items imaginable. Let's start with the armor itself, because understanding how it worked requires us to think about materials, science, and evolution simultaneously. The armored covering of Ankylosaurus wasn't like medieval knights' armor, separate metal plates strapped onto the body. Instead, it was osteoderms, bony plates that grew within the skin itself, similar to what we see in modern crocodiles and armadillos, but far more extensive and elaborate. These osteoderms came in different sizes and shapes across the body. Along the neck and back were large, flat plates called scutes, some measuring over a foot across. These overlapped slightly like roof shingles, providing comprehensive coverage while still allowing the animal to move. Between the large plates were smaller, knob-like osteoderms filling the gaps. Along the sides were rows of pointed spikes, each one a modified osteoderm, projecting outward to discourage attacks from the flanks. When you examine these osteoderms closely, you notice something fascinating about their structure. They're not solid bone all the way through. That would be too heavy. Instead, they have a dense outer layer of compact bone, while the interior is more porous, filled with a honeycomb-like structure of trabecular bone. This is brilliant engineering. The dense outer surface provides protection against impacts and bites, while the lighter interior reduces weight without sacrificing much strength. It's the same principle used in modern materials like corrugated cardboard or honeycomb panels in aircraft construction. Maximum strength for minimum weight. But there's more. The osteoderms weren't just passive armor. They were connected to the underlying bone and tissue by a network of blood vessels and nerves. This meant the animal could feel pressure on its armor, giving it sensory awareness of its surroundings even through the protective covering. Some osteoderms, particularly those around the neck, were fused directly to the underlying bone, creating an almost solid shield protecting vital areas. The head itself was a fortress. The skull of Ankylosaurus was massively reinforced, with thick bone covering the top and sides. Even the eyelids were armored. Small, bony plates protected the eyes when they were closed. The nostrils were positioned in complex, looping passages within the skull, possibly helping to warm and humidify air, but also protecting these vulnerable openings from attack. When you look at an Ankylosaurus skull, you're looking at an animal that had eliminated almost every potential weak point a predator might exploit. Now, let's talk about that extraordinary tail club, because this is where Ankylosaurus engineering reaches its pinnacle. The tail club of Ankylosaurus, particularly in large adults, could measure over 2 feet across and weigh perhaps 30 to 60 pounds, though estimates vary. It was composed of several large osteoderms that had fused together into a single, solid mass. This bony club was supported by the last several tail vertebrae, which themselves were specially modified. Here's where it gets really interesting from a biomechanical perspective. The vertebrae near the end of the tail were interlocking, limiting their flexibility. The tail could not bend much near the club itself. It was essentially a rigid handle, but further up the tail, perhaps 2/3 of the way along its length, the vertebrae had different articulation, allowing for significant side-to-side movement, while restricting up and down flexibility. This created a system very much like a medieval flail or a modern golf swing, a stiff section that can be swung rapidly from a flexible base. Scientists have actually studied the biomechanics of this system using computer models and physical simulations. In 2009, a team of researchers led by Victoria Arbour conducted detailed analysis of ankylosaur tail clubs. They found that the tail was optimally designed for delivering lateral strikes, swings from side to side rather than up and down. The muscles controlling this motion would have been substantial, anchored to robust processes on the vertebrae. When a large ankylosaurus swung its tail club, it would have worked something like this. The powerful muscles along the base of the tail would contract, initiating a rapid rotation. As this rotation traveled down the tail, the rigid section near the end would whip around at considerable speed. The heavy club at the very end, acting on the principle of angular momentum, would build up tremendous kinetic energy. When that club struck something, say the shin of an attacking tyrannosaur, all that energy would be transferred in a fraction of a second. How much force are we talking about? This is where modern physics helps us understand ancient combat. Researchers have created computer models of Ankylosaurus tail strikes, inputting data about the animal's size, the mass of the club, the length and flexibility of the tail, and the strength of the muscles. The results are sobering. A full-force strike from an adult Ankylosaurus could potentially generate forces in excess of 4,000 pounds per square inch at the point of impact. To put that in perspective, that's enough force to fracture large bones, not just bruise or crack them, actually break them. Tests on replicas striking bone analogs have shown that such impacts could indeed shatter the lower leg bones of large theropods. A tyrannosaur that received such a strike might not be killed immediately, but a broken leg in the Cretaceous world was often a death sentence. Unable to hunt effectively, unable to compete for food, the injured predator would likely starve or fall prey to infection. This is the kind of defense that makes attacking an Ankylosaurus a genuinely risky proposition for predators. It's not passive armor that simply makes the prey harder to kill. It's active defense that can seriously injure or disable the attacker. This fundamentally changes the predator-prey dynamic. Think about how a predator makes decisions. Hunting is always a risk-reward calculation. The prey provides energy and nutrients, but the hunt expends energy and risks injury. For most prey, the risk of injury is relatively low. A deer might kick you, a boar might cut you with its tusks, but these injuries are typically survivable and worth the risk when you're hungry. But an ankylosaurus, the risk of a broken leg, potentially fatal, dramatically changes the calculation. Predators would need to be extremely hungry, desperate, or have very effective hunting strategies to make attacking an ankylosaurus worthwhile. Now, let's consider the different species within the ankylosaur family, because Ankylosaurus, while the most famous, was just one of many armored dinosaurs that evolved this body plan. Each species shows interesting variations on the basic theme. Sicania, found in Mongolia, lived about 75 million years ago. It had particularly elaborate armor, with a heavily armored skull featuring a complex nasal passage system. Some researchers believe this nasal system might have helped Sicania survive in arid or dusty environments, filtering and conditioning air before it reached the lungs. The armor on Sicania's back featured distinctive keeled osteoderms, ridged plates that might have helped shed water or provided additional structural strength. Tarkia, another Mongolian ankylosaur, was one of the largest members of the family, rivaling Ankylosaurus in size. Tarkia had an especially robust tail club and some of the most heavily armored flanks known in the group. The spikes along its sides were prominent and sharp, arranged in multiple rows. This suggests Tarkia faced significant predation pressure, perhaps from the large tyrannosaurs that shared its environment. Euoplocephalus, from late Cretaceous North America, is one of the better-known ankylosaurs because we have relatively complete specimens. Euoplocephalus shows us details that help us understand ankylosaur biology. For instance, we can see that even the throat had some bony protection, small ossicles embedded in the skin of the neck that would help defend this vulnerable area if the animal was flipped onto its back. What's fascinating about comparing these different species is that they all converged on the same basic solution: comprehensive armor plus a tail weapon, but with variations suited to their specific environments and the threats they faced. It's like different countries independently developing tank designs that share fundamental features, but differ in details based on their specific military needs. This brings us to a profound question. Why did armor and offensive weapons evolve together in ankylosaurs? This pattern, heavily armored animals that also possess powerful weapons, seems to appear frequently in nature. Turtles have shells, and some have powerful biting jaws. Armadillos have armor and sharp claws. Porcupines have quills that are both defensive armor and offensive weapons when embedded in an attacker. The answer lies in evolutionary ecology and something called the escalation hypothesis. In any ecosystem, there's an ongoing arms race between predators and prey. Predators evolve to become better at hunting, faster, stronger, smarter. Prey responds by evolving better defenses. This creates selective pressure on predators to become even better, which creates pressure on prey to improve their defenses further. It's an escalating cycle that drives both groups to develop increasingly sophisticated adaptations. For ankylosaurs, this escalation led to comprehensive defense. But here's the key insight. Once you've invested heavily in armor, your mobility is typically reduced. You're slower, less agile. This makes escape less viable as a primary defense strategy. If you can't run effectively, you need another way to deter attackers. That's where the tail club comes in. It's not just defense, it's deterrence. A predator that knows attacking this prey might result in a broken leg is a predator that might choose different prey. There's also the question of intraspecific combat, fighting between members of the same species. Many animals use their defensive weapons not primarily against predators, but against each other, competing for mates or territory. Male deer use their antlers primarily against other males, not against wolves. Could ankylosaur tail clubs have served a similar function? The evidence is mixed. We don't have many fossils showing healed injuries to ankylosaur armor that would indicate regular combat between individuals. But absence of evidence isn't evidence of absence. It's possible that ankylosaurs engaged in ritualized combat that rarely resulted in serious injury, similar to how many modern armored animals fight. Two male ankylosaurs might have displayed their armor, posturing and perhaps exchanging relatively gentle tail swings to establish dominance without serious violence. What strikes me most about ankylosaurs is how they represent a fundamentally different survival strategy compared to other herbivores we've discussed. Therizinosaurs had enormous claws, but were relatively lightly built, and may have relied partly on being able to reach food others couldn't. Iguanodon had thumb spikes, but was also fairly agile, capable of running when necessary. Pachycephalosaurs were built for speed and, possibly headbutting contests, but could flee when threatened. Ankylosaurs made a different choice, evolutionarily speaking. They committed fully to the tank strategy. Make yourself so difficult to attack that predators choose easier prey. Accept the trade-off of reduced mobility in exchange for comprehensive protection, and ensure that any predator foolish enough to attack you pays a potentially deadly price. This strategy was clearly successful. Ankylosaurs thrived for millions of years, spreading across multiple continents. They were still going strong right up until the asteroid impact 66 million years ago that ended the age of dinosaurs. In the Hell Creek Formation, where we find the very last dinosaur communities before the extinction, Ankylosaurus was there, browsing peacefully on vegetation, its armor and tail club still formidable deterrents to the largest predators the world has ever known. When you really think about it, ankylosaurs show us something profound about evolution's creativity in solving the problem of predation. We've seen thumb spikes, giant claws, thick skulls, sails, and aquatic adaptations. Each represents a different solution to the challenges of Mesozoic life. The ankylosaur solution, comprehensive armor backed by devastating offensive capability, is perhaps the most straightforward, but it required precise engineering to work effectively. Every osteoderm had to be properly shaped and positioned. The tail club had to be exactly the right weight and supported by vertebrae with exactly the right structural properties. The muscles had to be strong enough to swing the club effectively. The sensory systems had to allow the animal to aim its strikes accurately. Get any of these elements wrong, and the whole system fails. The fact that ankylosaurs perfected this design and maintained it successfully for millions of years speaks to how well optimized their defensive system was. In many ways, the ankylosaurs represent the culmination of a particular evolutionary path, the ultimate expression of the armored herbivore strategy among dinosaurs. They couldn't be pushed much further without becoming unable to move at all. They had reached perhaps the practical limits of how much armor an active land animal could carry. But while some dinosaurs were evolving heavier and heavier builds, others were going in exactly the opposite direction. Some were becoming lighter, more delicate, developing features that would eventually lead to the evolution of flight. These creatures faced different challenges and evolved radically different solutions. So different that when their fossils were first discovered, scientists struggled to understand what they were looking at. We're about to meet dinosaurs that didn't walk on 2 legs or 4, but flew through the air on wings that shouldn't have worked according to everything paleontologists thought they knew about flight. The story of the 4-winged flyers opens a window into one of evolution's most remarkable transitions. Picture a small dinosaur, no larger than a crow, perched high in the canopy of an early Cretaceous forest in what is now China. The morning sun filters through the leaves, catching the iridescent sheen of its feathers, a glossy black that shimmers with hints of blue and green, like an oil slick or a raven's wing. But here's what makes this creature extraordinary. It has wings on all 4 limbs, not just arms modified into wings like a bird, but legs covered in long flight feathers as well, creating a four-wing configuration that aeronautical engineers would call a biplane design. This dinosaur launches itself from its perch, those four wings spreading wide. It doesn't flap powerfully like a modern bird. Instead, it glides, steering with subtle adjustments of its multiple wing surfaces, navigating between trees with remarkable precision. This is Microraptor Guy, and its discovery in the early 2000s revolutionized our understanding of how flight evolved, challenging assumptions paleontologists had held for over a century about the transition from ground-dwelling dinosaurs to the birds that fill our skies today. If you're captivated by these glimpses into evolution's experiments with flight, I'd appreciate if you'd like this video and subscribe. The story of how dinosaurs took to the air is one of the most fascinating chapters in the history of life on Earth. The story begins in 2003 when paleontologist Xu Xing and his colleagues published a description of an extraordinary fossil from the Liaoning province of China. The Liaoning deposits are famous among paleontologists. They're a treasure trove of exceptionally preserved fossils from the early Cretaceous period, about 120 million years ago. The fine-grained lake sediments captured incredible detail, preserving not just bones but soft tissues, including feathers, something extraordinarily rare in the fossil record. What made this particular fossil remarkable was immediately obvious. The creature was small, perhaps 30 inches from nose to tail, and covered in feathers. But it wasn't just the arms that had long flight feathers, the legs did too. Long, asymmetric feathers extended from both the forearms and the lower legs, creating four distinct wing surfaces. Nothing like this was known in any modern animal or any previously discovered fossil. The scientific community's reaction was mixed, fascination tinged with skepticism. Four wings? How would such a configuration even work? Birds have two wings, bats have two wings, pterosaurs had two wings. The two-wing design seemed to be the universal solution for powered flight in vertebrates. Why would evolution create a four-winged dinosaur? Was this some developmental anomaly? A weird individual rather than a typical member of its species? But then more fossils were found. Multiple specimens of Microraptor, all showing the same four-wing configuration. This wasn't a fluke or an oddity. This was how these animals were built. And that meant paleontologists needed to completely rethink their understanding of how flight evolved. Let's step back and consider what we know about Microraptor's biology, because the details are fascinating. When researchers examined these fossils under powerful microscopes, they could see the structure of the feathers with remarkable clarity. The feathers weren't just decorative, they were true flight feathers, with the asymmetric vein structure we see in modern flying birds. On one side of the central shaft, the vein is broader than on the other. This asymmetry is what makes flight possible. It allows air to flow over the feather in a way that generates lift. But here's something extraordinary that wasn't discovered until 2012. Using scanning electron microscopy, researchers examined the fossilized melanosomes, microscopic structures that contain pigment preserved in Microraptor's feathers. Based on the shape, size, and arrangement of these melanosomes, they could determine the actual color of the animal's plumage. The result? Microraptor was covered in glossy, iridescent black feathers, similar to modern crows or grackles. This tells us something important. Iridescent plumage in modern birds is almost always related to display, attracting mates or signaling to rivals. The fact that Microraptor had such elaborate coloration suggests that visual display was important in their social behavior. Perhaps males had more iridescent plumage than the females, used in courtship displays. This isn't just about how the animal flew, it's about how it lived, how it interacted with others of its species. Now, let's tackle the big question. How did Microraptor actually fly? This is where things get really interesting, because researchers have approached this question from multiple angles. comparative anatomy, aerodynamics, computer modeling, even building physical models and testing them in wind tunnels. The initial hypothesis was that Microraptor used a biplane configuration during flight. In early aircraft design, before engineers figured out how to build single-wing planes that were structurally sound and aerodynamically efficient, many planes used a biplane design, 2 wings stacked vertically, one above the other. This provided more lift and better structural support. Could Microraptor have positioned its 4 wings in a similar configuration, with the arm wings above and the leg wings below? Researchers created computer models testing different leg positions. If the legs were held out to the sides with the feet pointing backward, the leg feathers would create a lower wing surface while the arm feathers created an upper surface. Wind tunnel tests with physical models showed that this configuration could indeed generate lift and provide stable gliding flight. The small tail, also covered in feathers, could serve as a rudder for steering. But there were problems with this hypothesis. The leg position required for biplane flight would be awkward and possibly difficult to maintain for extended periods. Also, when you look at the hip joints and leg bones of Microraptor, they don't seem optimally designed for holding the legs in the splayed position that biplane flight would require. This led to alternative hypotheses. Perhaps Microraptor didn't maintain a static biplane configuration. Maybe it could adjust its leg position during flight, using different configurations for different maneuvers. During gliding, it might extend its legs to create more wing surface area. During landing approaches, it might tuck its legs closer to its body to reduce drag and improve maneuverability. This dynamic adjustment would be similar to how modern birds adjust their wing and tail positions for different flight behaviors. Another possibility is that Microraptor was primarily a glider rather than a powered flyer. Gliding is actually quite common in the animal kingdom. Flying squirrels, sugar gliders, and various other mammals glide using membranes stretched between their limbs. Some lizards and even some frogs have evolved gliding capabilities. Gliding is energetically cheap compared to powered flight. You use gravity and the structure of your gliding surfaces to stay aloft, rather than constantly expending energy flapping wings. For a small tree-dwelling dinosaur, gliding would be tremendously useful. Imagine Microraptor hunting insects in the forest canopy. It spots prey on a lower branch or on the ground. Instead of climbing down, which would be slow and energy intensive, it simply leaps and glides, steering with its wings and tail. This would allow it to cover territory efficiently, moving between trees to find food or escape from threats. The structure of Microraptor's feathers supports this gliding hypothesis. While they're asymmetric like modern flight feathers, they're not quite as strongly asymmetric as those of birds capable of sustained, powerful flight. This suggests Microraptor was a competent glider, but probably couldn't perform the kind of sustained, flapping flight that modern birds can manage. But here's where the story takes another turn, because Microraptor isn't the only bizarre flying dinosaur discovered in recent decades. In 2015, paleontologists described 2 closely related species that showed an entirely different approach to flight: Yi-Chi and Embopteryx. These small dinosaurs, also from China, but from slightly later in the Cretaceous, had membranous wings similar to bats, not feathered wings like birds. The fossils clearly showed a thin membrane of skin stretched between elongated fingers and a rod-like bone extending from the wrist. This rod, called a styloform element, provided support for the wing membrane, much like how a bat's fingers support its wing membrane. The animals were small, about the size of a pigeon, and appear to have been adapted for gliding or possibly limited powered flight through forests. This discovery was stunning because it showed that dinosaurs experimented with multiple solutions to the problem of flight. Birds, which are dinosaurs, evolve feathered wings, but before that lineage fully committed to the feathered wing design, there were apparently dinosaurs trying out membrane wings as well. It's as if evolution was running multiple experiments simultaneously, testing different configurations to see what worked best. The membrane wings of Yi-Chi and Embopteryx ultimately didn't win the evolutionary competition. They went extinct, while the lineage that led to modern birds thrived. But their existence shows us that evolution is a process of trial and error. Not every experiment succeeds in the long term, but each experiment teaches us something about the possibilities and constraints of biological design. This brings us to one of the biggest debates in paleontology. How did flight evolve in the first place? There are two main competing hypotheses, often called the ground-up and trees-down scenarios. The ground-up hypothesis suggests that the ancestors of flying dinosaurs were fast-running, ground-dwelling predators. As they ran and leapt to catch prey or escape predators, individuals with feathers on their arms that could generate a bit of extra lift or thrust would have an advantage. Over many generations, these feathers became larger and more specialized, eventually becoming true wings. In this scenario, flight evolved from running and jumping. The trees-down hypothesis proposes that the ancestors were tree-dwelling animals. They initially climbed and then leaped from branch to branch. Any feature that could slow their descent or allow them to glide between trees would be advantageous. Feathers that acted as simple airfoils would help. Over time, these gliding structures became refined into wings capable of powered flight. In this scenario, flight evolved from gliding. Microraptor provides evidence for the trees-down hypothesis. Its four-wing configuration makes much more sense for an animal that's gliding between trees than for one running on the ground. You can't run effectively with long feathers on your legs. The fact that Microraptor had curved claws suited for gripping branches also supports the idea that it was a tree dweller. But the debate isn't settled. Different lineages might have taken different paths to flight. Maybe some dinosaurs developed flight through ground-up methods while others went trees down. Evolution doesn't follow a single script. It explores all available options. And sometimes multiple paths lead to similar destinations. Modern biomechanical studies continue to refine our understanding. Researchers have built robotic models of Microraptor that can actually fly, programmed with different wing beat patterns to test what might have been aerodynamically viable. They've used computational fluid dynamics, sophisticated computer simulations that model airflow, to analyze how air would have moved over Microraptor's wings during different maneuvers. These studies suggest that Microraptor was probably capable of more than just passive gliding. It might have been able to perform controlled, directed flights with some active flapping, though probably not sustained flapping flight over long distances. It would have been more maneuverable in complex, cluttered environments like forests than modern birds, able to make sharp turns and navigate between closely spaced obstacles. Think about what this means for our understanding of the early Cretaceous ecosystem. The forests weren't just filled with ground-dwelling dinosaurs. The canopy was alive with small, feathered dinosaurs gliding and flying between trees, hunting insects, probably competing with early true birds for ecological niches. It was a three-dimensional ecosystem, far more complex than we once imagined. The discovery of four-winged dinosaurs also helps us understand the transition to modern birds. Birds didn't appear suddenly, fully formed. There was a long period of experimentation where different configurations were tested. Four wings worked for Microraptor in its particular ecological niche. But as dinosaurs evolved toward more powerful, sustained flight, the two-wing configuration proved more efficient. The leg feathers were probably lost because they interfered with ground locomotion and weren't necessary once the arm wings became powerful enough for sustained flight. This pattern, multiple experimental forms giving way to a single optimized design, is common in evolution. When a new capability first appears, there's often an explosion of diverse forms as different lineages try different approaches. Eventually, one design proves most effective and dominates, while the others go extinct. We see this pattern in the evolution of flight, in the evolution of eyes, in the evolution of almost every major biological innovation. What continues to amaze me is how much information can be extracted from these fossils. We're not just looking at bones, we're seeing the actual color of feathers, understanding the aerodynamics of flight configurations that no longer exist, inferring behavior and ecology from skeletal structure and environmental context. Every fossil tells a story, but some fossils, like Microraptor, tell extraordinarily rich stories that illuminate entire chapters of evolutionary history. Can you imagine being the first paleontologist to examine that Microraptor fossil, seeing those four wings preserved in the stone, realizing you're looking at something no one had ever conceived of before? These moments of discovery, when scientists realize they're seeing something that challenges everything they thought they knew, are what drive scientific progress. They remind us that nature is far more creative, far more willing to experiment than we can predict. The four-winged dinosaurs also remind us that extinction isn't necessarily a sign of failure. Microraptor was successful for millions of years. It filled an ecological niche effectively. The fact that its particular body plan didn't survive to the present day doesn't mean it was poorly designed. It means that conditions changed, competition shifted, and other designs proved more adaptable to new circumstances. In the moment, in its own time, Microraptor was a triumph of evolutionary engineering. While these small, feathered dinosaurs were mastering the skies through lightweight construction and sophisticated wing designs, other dinosaurs at the opposite end of the size spectrum were dealing with entirely different challenges. The largest land animals ever to walk the earth faced problems that small flyers never encountered, supporting massive body weight, processing enormous quantities of food, and developing features that, in some cases, seem almost too bizarre to be functional. These giants developed their own set of strange adaptations, from spikes and sails to feeding mechanisms that challenge our understanding of what's possible in vertebrate biology. Imagine standing at the base of a creature so tall that you have to crane your neck just to see where its body meets the sky. It's a sauropod, one of those iconic long-necked dinosaurs that have captured our imagination since we first discovered their fossils. But as you look up, you notice something unexpected. Running down the entire length of its neck and back is a double row of spines, each one tall enough to reach your chest, creating what looks like a living picket fence stretching from head to hips. This isn't decoration. These spines are bone, extensions of the vertebrae, covered in life by skin or perhaps supporting some kind of sail or display structure. This is a Margosaurus, and it represents something profound about sauropod evolution. We tend to think of these giant dinosaurs as following a simple template: small head, impossibly long neck, massive barrel-shaped body, long tail, four pillar-like legs. But within this basic framework, evolution created astonishing variations. Some sauropods had teeth arranged in patterns that would make a modern dentist marvel. Others had necks surprisingly short for their group. And one species may have been the heaviest animal ever to walk on land, pushing the absolute physical limits of what's possible for a terrestrial creature. If you're finding these explorations of evolutionary extremes as captivating as I do, I'd be grateful if you'd take a moment to like this video and subscribe. The story of how sauropods diversified into such strange forms reveals the incredible creativity of natural selection when given vast timescales to experiment. Let's begin with the Margosaurus kazaui, discovered in 1984 in Argentina. When paleontologist Jose Bonaparte and his team first examined the vertebrae of this animal, they must have been startled. The neural spines, those projections extending upward from each vertebra, were extraordinarily elongated, particularly along the neck. Some of these spines reached lengths of 2 feet or more, creating paired rows that ran like parallel rails down the animal's neck and forward back. What makes a Margosaurus especially intriguing is that we're still debating what these spines supported in life. There are 3 main hypotheses, and each tells us something different about how this animal lived. The first hypothesis is that the spines supported a sail, similar to what we discussed with Spinosaurus, but with a crucial difference. Spinosaurus had a single row of spines. Amargasaurus had two parallel rows. If these supported sails, the structure would have been bifurcated, two separate sails running side by side down the neck and back. Such a structure could have been used for thermoregulation, helping the animal heat up or cool down by controlling blood flow to the sails. In the warm Cretaceous climate of what is now Patagonia, having an efficient cooling system would have been valuable, especially for an animal generating heat through the metabolism of a multi-ton body. The second hypothesis suggests the spines were covered with a thick pad of fat or muscle, creating a humped appearance similar to modern camels or bison. This would have served as energy storage, allowing Amargasaurus to survive periods when food was less abundant. For an herbivore in an environment with seasonal variation, such energy reserves would provide a significant survival advantage. The third hypothesis is perhaps the most visually striking. The spines were covered only in skin and stood exposed, like a palisade of bony projections. In this interpretation, they would have been primarily for display, making the animal look larger and more impressive to potential mates or rivals. The spines might have been brightly colored or patterned, serving as visual signals that communicated age, health, and genetic fitness. Which interpretation is correct? We may never know with certainty, but each scenario is plausible based on what we understand about animal biology and evolution. What we do know is that Amargasaurus was relatively small for a sauropod, measuring about 30 feet in length, modest compared to its larger relatives. Perhaps those spines helped this smaller sauropod compete in an environment filled with much larger animals, either by providing physiological advantages or by making it appear more formidable than its actual size would suggest. The spines also raise interesting questions about biomechanics. Having such tall projections along the neck would affect how the animal could move its head. The neck would have been less flexible than in other sauropods, potentially limiting its feeding range. This suggests Amargasaurus might have been a more selective browser, perhaps specializing in particular types of vegetation that didn't require extensive neck mobility to access. Now, let's shift our attention to something completely different, a sauropod whose most remarkable feature wasn't on its back or neck, but in its mouth. Nigersaurus takedi, discovered in the West African nation of Niger, possessed one of the most unusual skull structures ever found in a dinosaur. Picture a sauropod skull, but instead of the typical elongated shape we see in most species, imagine it's been compressed and widened, creating a broad, squared-off muzzle. Now, pack that muzzle with teeth, not just a few dozen, but hundreds of them. Nigersaurus had more than 500 teeth arranged in tightly packed columns, with multiple replacement teeth waiting behind each functional tooth, ready to move forward as the front teeth wore down. The arrangement has been compared to a vacuum cleaner or a lawnmower. The teeth formed a broad, straight-cutting edge at the front of the mouth, like a biological hedge trimmer. This wasn't for chewing. The teeth were too delicate for that. Instead, they were for cropping, for slicing through soft vegetation with swift, efficient strokes. When paleontologist Paul Sereno and his team analyzed Nigersaurus in detail, using CT scans to see inside the skull, they discovered something remarkable. At any given time, the animal had about 50 to 60 teeth in active use in each jaw, upper and lower. But behind these functional teeth, lined up like ammunition waiting to be loaded, were hundreds more replacement teeth. As the front teeth wore down from constant use, and they would have worn down quickly given the abrasive nature of plant material, new teeth would migrate forward to take their place. This rapid tooth replacement system is extreme even by dinosaur standards. Most dinosaurs replace their teeth throughout their lives, but Nigersaurus appears to have had one of the fastest replacement rates known. Estimates suggest that each tooth position might have been replaced every 14 days or so. That means Nigersaurus was constantly growing new teeth, a biological conveyor belt ensuring it always had sharp cutting surfaces for feeding. The structure of the skull also tells us about feeding behavior. Nigersaurus had a downward tilted head posture, with the tooth batteries oriented horizontally. This suggests it fed on ground-level vegetation, sweeping that broad muzzle back and forth like a living lawnmower, cropping vast quantities of ferns, horsetails, and other low-growing plants. It was probably a bulk feeder, processing huge volumes of vegetation rather than being selective about what it ate. The teeth themselves were asymmetric, with the outer edge longer than the inner edge, creating a cutting surface that would have been highly efficient for slicing through soft plant material. But they were also quite thin and delicate. Nigersaurus probably avoided tough, woody vegetation that might have damaged these specialized teeth. What's fascinating is how this represents a completely different feeding strategy from other sauropods. Most sauropods were high browsers, using their long necks to access vegetation that other herbivores couldn't reach. Nigersaurus, with its relatively short neck and specialized ground-level feeding apparatus, had evolved to exploit a different food source entirely. It was occupying an ecological niche more similar to modern grazing animals like wildebeest or bison than to other sauropods. This brings us to one of the most paradoxical sauropods ever discovered, Brachytrachelopan maysai, whose name literally means short-necked Pan, referring to the Greek god Pan and the unusually short neck that define this species. Found in Argentina and described in 2005, Brachytrachelopan challenges one of the fundamental assumptions about sauropod biology, that long necks are a defining characteristic of the group. Don't misunderstand, Brachytrachelopan's neck wasn't short in absolute terms. It was still several feet long, but for a sauropod, it was remarkably abbreviated, measuring only about 40% of the animal's total body length. In most sauropods, the neck accounts for a much larger proportion of body length, sometimes exceeding 50 or even 60%. Why would a sauropod evolve a shorter neck? This seems counterintuitive given that the long neck is such a successful adaptation, allowing these animals to access food that's out of reach for other herbivores. The answer lies in ecological specialization and competition. Brachytrachelopan lived during the late Jurassic period in what is now Patagonia. This was an environment filled with sauropods of various sizes, all competing for vegetation. In such a competitive environment, there would be advantages to exploiting food sources that other sauropods couldn't easily access. While long-necked sauropods were browsing on high vegetation, Brachytrachelopan could have specialized in mid-level or even low vegetation, using its shorter neck to feed more efficiently in dense undergrowth, where a long neck might be cumbersome. The shorter neck would also have had biomechanical advantages. A long neck creates significant stress on the vertebrae, muscles, and ligaments supporting it. By having a shorter neck, Brachytrachelopan would have reduced these stresses, potentially allowing it to move its head more quickly and with greater precision when feeding. It might have been able to browse more selectively, choosing specific plants or plant parts rather than engaging in the bulk feeding strategy typical of larger sauropods. This discovery reminds us that evolution isn't always about pushing features to extremes. Sometimes the optimal adaptation is to moderate a characteristic that's extreme in related species. Brachytrachelopan shows us that even within a group defined by a particular trait, in this case, long necks, there's room for variation and specialization. Now, let's turn to the opposite extreme of sauropod evolution. While Brachytrachelopan was relatively modest in size, there were sauropods that pushed the boundaries of how large a land animal can possibly be. And one of the most impressive is Dreadnoughtus schrani, described in 2014 from fossils found in Argentina. The name Dreadnoughtus means fears nothing, a reference to the massive early 20th century battleships, and to the idea that an animal this large would have had nothing to fear from predators. And make no mistake, Dreadnoughtus was enormous. The specimen described in 2014 was still growing when it died, and yet it's estimated to have weighed approximately 65 tons. That's about as much as a dozen African elephants. It's heavier than most commercial airliners. And remember, this animal was still not fully grown. What makes Dreadnoughtus particularly important, scientifically, is that the discovered skeleton was remarkably complete. About 45% of the animal's bones were recovered, including many from the limbs and limb girdles. This is crucial because these are the bones that bear weight, and having them allows scientists to estimate the animal's mass with much greater confidence than is possible with more fragmentary specimens. When paleontologists analyze how such massive animals could exist, they're essentially working at the intersection of biology, physics, and engineering. There are hard physical limits to how large a land animal can be, imposed by the constraints of bone strength, muscle power, and the laws of physics governing weight and support. Consider the legs. Dreadnoughtus had femurs, thigh bones, that measured over 6 feet in length and were massively robust, with enormous cross-sectional areas to bear the tremendous weight pressing down on them. The bones weren't solid. Like all dinosaur bones, they had internal air spaces, called pneumatic cavities, that reduced weight without sacrificing too much strength. This is similar to modern bird bones and represents an adaptation that was crucial for allowing dinosaurs to achieve such large sizes. The feet were also remarkable. Each foot had to support roughly a quarter of the animal's weight. Imagine a 16-ton load resting on 4 feet, each one distributing that force across a relatively small surface area. The bones of the feet were arranged in a columnar structure, stacked vertically to transmit force directly downward. The foot had a heel pad, similar to elephants, made of fibrous tissue that compressed under weight, helping to cushion each step and distribute pressure more evenly. But size creates challenges beyond just support. How does an animal this large get enough to eat? A 65-ton herbivore needs an enormous amount of plant material daily. Estimates suggest perhaps 200 to 300 pounds of vegetation per day, possibly more. Dreadnoughtus would have spent most of its waking hours feeding, using its long neck to sweep through vegetation like a biological crane, stripping branches and swallowing them with minimal chewing. The digestive system would have been extensive. Sauropods appear to have used a fermentation-based digestive strategy similar to modern ruminants, but probably occurring in the intestines rather than the stomach. The gut would have been filled with microorganisms that broke down tough plant cellulose, extracting nutrients that the animal's own enzymes couldn't access. This process takes time and space, which explains the barrel-shaped body. It's essentially a mobile fermentation chamber. There's also the question of metabolism. For decades, scientists debated whether dinosaurs were warm-blooded like mammals or cold-blooded like modern reptiles. The current consensus is that large dinosaurs like Dreadnoughtus probably had elevated metabolic rates compared to modern reptiles, though perhaps not as high as mammals. Their sheer size would have helped maintain body temperature through inertial homeothermy, being so large that they heated up and cooled down very slowly, maintaining relatively stable internal temperatures even without the high metabolic rates of smaller warm-blooded animals. What's particularly interesting is thinking about the growth rate required to reach such size. Dreadnoughtus didn't start at 65 tons. It hatched from an egg, probably weighing just a few pounds. Studies of bone histology, the microscopic structure of bone tissue, suggest that sauropods grew rapidly during their early years, possibly adding several tons per year during peak growth periods. This requires not just abundant food, but also efficient digestion and metabolism to convert all that plant material into body mass. The existence of animals like Dreadnoughtus also tells us about the Mesozoic environment. To support such gigantic herbivores, there must have been incredibly productive plant communities, forests and plains that could produce vast quantities of vegetation sustainably. The climate must have been favorable, warm and humid enough to support lush plant growth year-round or nearly so. And there must have been relatively few physical barriers in the environment, allowing these massive animals to move around to find food. Why did evolution push sauropods to such extremes of size? There are several advantages to being enormous. Large animals have fewer predators. Even the biggest predatory dinosaurs would think twice about attacking a healthy adult Dreadnoughtus. Large animals are also more efficient at regulating body temperature, as mentioned earlier, and large size allows access to food sources that smaller animals can't reach, the highest vegetation and the tallest trees. But there are also costs. Large animals need more food, grow more slowly, and typically have lower reproductive rates. They're more vulnerable to environmental changes that affect food availability. And as we've seen, there are physical limits to how large a land animal can become, imposed by bone strength and the square cube law. As an animal gets larger, its volume and mass increase faster than its surface area and structural support. Dreadnoughtus may have been near those limits. We don't know if there were sauropods significantly larger. Claims have been made based on fragmentary fossils, but without more complete specimens, it's hard to verify. What we can say is that Dreadnoughtus represents one of evolution's most impressive achievements in sheer scale. Have you ever tried to imagine what it would be like to see one of these giants? Not in a museum where we see only bones, but alive, breathing, moving through a Cretaceous landscape. The ground would tremble with each footfall. The sound of its feeding, branches breaking, vegetation being stripped, would echo through the forest. And the sheer presence, the almost overwhelming reality of an animal that massive, would be unlike anything in our modern world. These four sauropods, a Margosaurus with its mysterious spines, Nigersaurus with its remarkable tooth batteries, Brachytrachelopan with its unexpectedly short neck, and Dreadnoughtus with its almost incomprehensible mass, show us how a single body plan can be modified in the countless ways. They all share the basic sauropod blueprint, but each has taken that blueprint and adapted it to solve different problems, exploit different resources, survive in different environments. This pattern of diversification within a basic framework is one of evolution's hallmarks. It's not creating entirely new designs from scratch for each species. It's taking existing structures and modifying them, sometimes in small ways, sometimes dramatically, to suit different ecological roles. The result is the spectacular diversity we see in the fossil record, with each species representing evolution's solution to a particular set of challenges. As we've journeyed through these 8 stories of dinosaurian strangeness, from thumb-spiked herbivores to sail-backed predators, from head-butting pachycephalosaurs to giant-clawed therizinosaurs, from armored tanks to 4-winged flyers, and finally to these remarkable sauropods, we've seen how evolution explores every possibility, creates solutions we might never predict, and produces a natural world far stranger and more wonderful than any fiction. These weren't failed experiments or evolutionary dead ends. They were successful animals, thriving in their worlds for millions of years, and their strangeness wasn't a flaw, but a feature, each bizarre adaptation serving purposes that made perfect sense in the context of their lives. What can these creatures teach us about the nature of life itself, about diversity, adaptation, and the creative power of evolution? That's the question we'll explore as we bring our journey to a close. We've spent the last hour and a half together, exploring creatures that challenge our expectations at every turn. Dinosaurs with thumb spikes that were mistaken for nose horns, semi-aquatic predators with sails on their backs, animals with skulls built like battering rams, herbivores carrying claws that could disembowel predators, living tanks with bone clubs for tails, 4-winged flyers, and giants that push the very limits of what's physically possible for a land animal. But here's the question that ties all these stories together. What does weird really mean? When we call these dinosaurs bizarre or strange, are we describing them accurately, or are we revealing something about our own limited perspective? Because to the creatures that possess these features, to the ecosystems they inhabited, nothing about them was weird at all. They were simply adapted, successful, perfectly suited to their worlds. If this exploration has given you new perspectives on life, evolution, and the creativity of nature, I'd be grateful if you'd like this video and subscribe. There are so many more stories waiting to be told, and I hope you'll join me for them. Let's think about what we mean when we call something weird or bizarre. Usually, we're comparing it to what we consider normal, to the animals we're familiar with, to the patterns we expect, to designs that make immediate sense to our modern sensibilities. But this comparison is fundamentally flawed because it assumes our current moment in time, our current ecosystem, represents some kind of biological standard against which all other life should be measured. It doesn't. The Earth today, with its particular climate, its specific arrangement of continents, its current cast of species, is just one frame in a film that's been running for over 4 billion years. The Mesozoic era, when dinosaurs dominated, lasted for 186 million years, far longer than mammals have been the dominant large land animals. During that vast span, the world was different. The climate was warmer, the continents were in different positions, the plants were different. For much of the Mesozoic, there were no flowers, no grasses, none of the flowering plants that dominate modern landscapes. In that world, the adaptations we've explored weren't bizarre. They were responses to real evolutionary pressures, solutions to genuine problems. The thumb spike of Iguanodon wasn't a weird quirk. It was a tool that helped the animal access food and defend itself in an environment filled with competitors and predators. Spinosaurus's semi-aquatic lifestyle wasn't strange. It was an exploitation of a rich ecological niche, the abundant fish in Cretaceous rivers, that other large predators weren't effectively utilizing. This shift in perspective is crucial. When we study extinct life, we're not looking at failed experiments or evolutionary dead ends. We're looking at animals that were successful by the only measure that matters. They survived long enough to reproduce, passing their genes to the next generation over and over for millions of years. The fact that they're extinct now doesn't diminish their evolutionary success. It simply means that conditions changed in ways they couldn't adapt to, or that they were victims of catastrophic events beyond any organism's ability to survive. Let's consider what recent discoveries have taught us about how profoundly our understanding can change. When I started this journey through paleontology years ago, Spinosaurus was thought to be a large, land-dwelling predator with an interesting sail. The idea that it might be semi-aquatic would have been considered radical, probably dismissed. But new fossils, new analytical techniques, and researchers willing to challenge assumptions have completely revolutionized our understanding. The 2020 discovery of Spinosaurus's swimming tail was particularly transformative. It wasn't speculation anymore. It was direct evidence of an aquatic adaptation. Similarly, our understanding of pachycephalosaurs has evolved. The certainty that those thick skulls were for headbutting has given way to nuanced discussion of multiple possible functions. The revelation that what we thought were 3 different species might actually be growth stages of a single species reminds us how careful we must be about interpreting fragmentary fossils. Microraptor's 4 wings showed us that the evolution of flight was more complex than we'd imagined, with multiple experimental configurations being tested by evolution before the 2-wing design of modern birds became dominant. And the discovery of Yi-Chi and Embopteryx, dinosaurs with bat-like membrane wings, proved that evolution was even more creative than we'd suspected, trying out radically different solutions to the challenge of flight. These ongoing discoveries teach us humility. They remind us that our current understanding, however sophisticated, is provisional. Future paleontologists will undoubtedly look back at what we know today and find errors, oversimplifications, misinterpretations. And that's okay. That's how science works. We make the best inferences we can with the evidence available, We test our hypotheses, and we remain open to revision when new evidence emerges. But beyond the specific facts about individual species, these strange dinosaurs teach us broader lessons about the nature of life and evolution itself. First, they demonstrate the power of deep time. When evolution has millions of years to work, when natural selection operates across thousands and thousands of generations, the cumulative changes can be extraordinary. Small modifications, each providing a tiny advantage, compound over time to produce dramatically different forms. The transition from carnivorous theropods to herbivorous therizinosaurs didn't happen overnight. It was a gradual process, spanning millions of years and probably many intermediate species whose fossils we haven't found yet. Second, these dinosaurs show us that evolution is opportunistic. It doesn't plan ahead or work towards some predetermined goal. It simply favors whatever works right now, in this moment, in this environment. Sometimes this leads to solutions that seem inefficient or overly complicated to our engineering-minded perspectives. Therizinosaurs are herbivores built on a carnivore chassis. That's not the most elegant design. If you were designing an herbivorous dinosaur from scratch, you probably wouldn't start with a theropod body plan. But evolution doesn't design from scratch. It modifies what already exists, and the results, while sometimes unexpected, can be remarkably successful. Third, we learn about adaptive radiation and ecological specialization. In the sauropods, we see a basic body plan: long neck, large body, long tail, being modified in myriad ways to exploit different food sources and survive in different environments. Nigersaurus with its vacuum cleaner mouth feeding at ground level. Brachytrachelopan with its shorter neck browsing mid-level vegetation. Amargasaurus with its spine serving purposes we're still debating. Each represents a different solution within the sauropod framework, showing how a single ancestral lineage can diversify to fill multiple ecological roles. Fourth, these creatures teach us about evolutionary arms races. The elaborate defenses of Ankylosaurus, comprehensive armor backed by a devastating tail weapon, didn't evolve in a vacuum. They evolved in response to predation pressure from increasingly large and powerful predators. Those predators, in turn, may have evolved larger size and more powerful jaws, partly in response to increasingly well-defended prey. This back and forth, this escalation, drives both predators and prey to develop increasingly sophisticated adaptations. And fifth, perhaps most importantly, these dinosaurs teach us about biodiversity and the importance of variation. In any ecosystem, the species that survive are often not the strongest or the fastest in some absolute sense, but the ones best suited to their particular niche. Diversity creates resilience. When environments change, when catastrophes strike, ecosystems with high biodiversity are more likely to have some species that can survive and adapt to new conditions. The dinosaurs we've explored tonight were all successful in their own right, but they also contributed to the overall health and resilience of their ecosystems. Each strange adaptation, each unusual feature, represented a different way of being, a different strategy for survival, and that diversity made Mesozoic ecosystems robust and dynamic. But let's be honest about what we don't know, because the gaps in our knowledge are as fascinating as what we do understand. There are profound mysteries that remain unsolved, questions that keep paleontologists awake at night. We still don't fully understand how dinosaurs regulated their body temperature. Were they warm-blooded like mammals? Cold-blooded like modern reptiles, or something in between? Mesothermic, perhaps, maintaining elevated body temperatures through a combination of metabolic heat and behavioral regulation. Different species might have had different strategies, and we're still piecing together the evidence. We have limited understanding of dinosaur social behavior. Did pachycephalosaurs really engage in headbutting contests? Or were those skulls primarily for display? How did therizinosaurs use those enormous claws in their daily lives? Did ankylosaurs live in groups, or were they solitary? Without the ability to observe living animals, we must infer behavior from fossilized bones, trackways, and occasional nesting sites. A challenging endeavor. We don't know the full range of colors and patterns that adorn these animals. While we've made remarkable progress with fossils that preserve melanosomes, we know Microraptor was iridescent black, for instance. Most dinosaurs haven't left behind such detailed preservation. What colors were Spinosaurus's sail? Was Amargasaurus's spine structure brightly patterned? These visual details, so important for display and communication, are largely lost to time. And there's the persistent question of what other strange dinosaurs remain to be discovered. We've found thousands of dinosaur species, but paleontologists estimate this represents only a fraction, perhaps a small fraction, of all the species that existed during the Mesozoic era. For every fossil we find, there might be dozens or hundreds of species that lived and died, without leaving any trace we've discovered yet. What bizarre adaptations await in rocks we haven't yet excavated? What surprising creatures will future paleontologists unearth? Think about this. Every strange dinosaur we've discussed tonight was at one point unknown to science. Someone had to discover those first fossils, puzzle over what they meant, gradually build an understanding of these creatures. And that process continues. Right now, somewhere in the world, there are fossils weathering out of rock faces, waiting to be found. Some of them will represent entirely new species, possibly with features we haven't imagined yet. This ongoing discovery is one of the joys of paleontology. Unlike some sciences where the fundamental questions might be close to answered, paleontology remains a field of constant surprise. The Earth still holds countless secrets, and patient researchers continue to reveal them, one fossil at a time. Let me share with you one of my favorite aspects of studying these ancient creatures. They help us see the present more clearly. When you understand that Earth's history includes animals as diverse as the ones we've explored tonight, it changes how you look at modern life. The platypus, that strange egg-laying mammal with a duck's bill, suddenly seems less odd. After all, we're talking about a world that once had four-winged dinosaurs. The giraffe's long neck, which might seem improbable, makes perfect sense when you've studied sauropods with necks 3 times as long. Even humans, with our oversized brains and bipedal stance, are just another example of evolution creating something unique. This perspective is valuable. It reminds us that life is endlessly creative, that evolution will explore any possibility that provides an advantage, that the natural world is far stranger and more wonderful than we typically appreciate. It also reminds us of something sobering. Extinction is real, and it's permanent. Every one of the creatures we've discussed tonight is gone. Iguanodon, Spinosaurus, Pachycephalosaurus, Therizinosaurus, Ankylosaurus, Microraptor, Amargasaurus, Nigersaurus, Brachytrachelopan, Dreadnoughtus, all extinct, along with every other non-avian dinosaur. They thrived for millions of years, these remarkable animals, and then they were gone, victims of the asteroid impact that ended the Cretaceous period 66 million years ago. That extinction event reminds us how fragile life can be, how even the most successful species can vanish if conditions change dramatically enough. But it also demonstrates life's resilience. The asteroid impact killed the non-avian dinosaurs, but it didn't kill all dinosaurs. Birds, which are living dinosaurs, descendants of small theropods, survived. And in the aftermath, they diversified, filling ecological niches left vacant by their extinct relatives, eventually producing the more than 10,000 bird species we have today. So, the legacy of dinosaurs isn't just fossils in museums. It's there every time you see a robin pulling a worm from your lawn, or hear a crow calling from a tree, or watch a hummingbird hovering at a flower. Those are dinosaurs, modified by 66 million years of evolution. But dinosaurs nonetheless. The strange creatures we've explored tonight have living descendants, and that's both humbling and inspiring. As we reach the end of our journey through these bizarre adaptations, I want to leave you with one final thought. The natural world is not a finished product. Evolution continues, right now, all around us. Species are adapting to new environments, developing new traits, responding to selective pressures we might not even notice. In millions of years, if any intelligent species exist to study them, the animals of our time might seem just as strange, just as wonderful, just as improbable as Spinosaurus or Therizinosaurus seem to us. What will paleontologists of the distant future make of elephants with their trunk noses? Of whales, which are mammals that return to the ocean and evolve to breathe air while living underwater? Of humans, with our enormous brains housed in fragile skulls, using tools and language to dominate our planet in ways no other species has? We can't know, but we can appreciate that we are part of the same story, the same grand experiment in adaptation and survival that produced all the creatures we've met tonight. We're not separate from nature, observing it from the outside. We're participants in it, products of the same evolutionary processes that created thumb spikes and sailbacks and dome skulls and giant claws. Have you ever felt a sense of connection to these ancient animals? Despite the hundreds of millions of years that separate us, despite the alien nature of their world, there's something profound about recognizing that we share common ancestry, that the same forces that shape them also shaped us, that we're all part of one continuous story of life on Earth. The dinosaurs got weird because evolution rewards innovation, because there are countless ways to survive, because diversity itself is valuable. And in their weirdness, in their wonderful strangeness, they show us something essential about the nature of life. It's not about perfection, it's about adaptation. It's not about following rules, it's about solving problems. It's not about being normal, it's about being successful in your particular circumstances. As you drift towards sleep tonight, perhaps you'll dream of these ancient worlds, of forests filled with creatures unlike anything alive today, of thumb-spiked herbivores browsing on cycads and ferns, of sail-backed hunters wading through Cretaceous rivers, of armored tanks lumbering through landscapes that would one day become our world, of tiny four-winged dinosaurs gliding through canopy shadows, their feathers catching dappled sunlight. These weren't monsters or fantasies. They were real animals, living real lives, in a real world that was as complex and beautiful as our own. They ate, slept, reproduced, competed, cooperated, struggled, and succeeded. For millions upon millions of years, they were here, part of Earth's story. And though they're gone now, their fossils remain, silent testaments to the creative power of evolution, to the resilience of life, to the endless variations nature can produce when given time and opportunity. The story of life on Earth is far from over. New chapters are being written right now as species adapt to changing climates, as evolution continues its patient work of modification and innovation. What strange creatures await in the deep future? What bizarre adaptations will emerge in response to challenges we can't yet imagine? We won't be here to see them, but they'll come, as surely as Spinosaurus and Therizinosaurus and all the others emerged in their time. And perhaps, millions of years from now, some future intelligence will study our fossils with the same wonder, the same curiosity, the same desire to understand that drives our study of dinosaurs. They'll puzzle over our strange features, our upright stance, our large brains, our tiny teeth. They'll debate how we lived, what drove our evolution, why we looked the way we did. And if they're wise, they'll recognize that we, like the dinosaurs, were products of our time, adapted to our environment, successful by the standards that matter in evolution. For now, we have these fossils, these windows into vanished worlds. We have the work of dedicated paleontologists who spend their lives piecing together fragments of the past. We have museums where we can stand before these ancient skeletons and feel, however briefly, a connection across the vast gulf of time. And we have our imaginations, capable of bringing these creatures to life in our minds, of envisioning worlds stranger than dreams. Thank you for joining me on this journey through the weird and wonderful world of dinosaurs. Thank you for your curiosity, your patience, your willingness to spend these hours exploring creatures that have been gone from Earth for 66 million years. I hope these stories have shown you that the natural world, past and present, is far richer and more surprising than we often realize. I hope they've inspired a sense of wonder at the creative power of evolution. And I hope they've reminded you that strangeness isn't a flaw, it's a feature, evidence of life's endless capacity for innovation and adaptation. The universe of ancient life contains countless more stories waiting to be told. Strange sea creatures that swam in primordial oceans, early mammals that scurried through the undergrowth while dinosaurs ruled, the evolution of flight, of intelligence, of social behavior, the rise and fall of entire ecosystems. Each story offers insights into how life works, how it changes, how it persists against all odds. I hope you'll join me again as we continue exploring these mysteries together. Until then, rest well, dream of ancient worlds, and remember that the natural world, in all its weird and wonderful diversity, is still here, still creating new chapters in the oldest story ever told, the story of life on Earth. Sleep peacefully and let your mind wander through forests filled with creatures that time has taken from us, but imagination can restore. Good night.